Hello and welcome to this video on the essential machine learning algorithms every AI engineer should know. Today, we'll go through the different types of machine learning algorithms grouped under supervised, unsupervised, and other specialized categories. By the end, you will have a solid understanding of the key algorithms and their implementation. Let's get started. First, let's start with supervised learning algorithms. These algorithms are trained on labeled data, which means we already know the target outcomes. Supervised learning is often used for tasks like prediction, classification, and regression. Here are the main algorithms you should know under supervised learning. So first, main category is regression algorithms, which has linear regression, ridge and lasso regression, polynomial regression, and then we have classification algorithms which has logistic regression, k nearest neighbors or KNN, support vector machines SVM, decision trees, random forest, gradient boosting, and naive Bayes. So these are the main algorithms that we will be looking over in supervised learning algorithms. Next, let's go to unsupervised learning algorithms. These algorithms work with unlabeled data, discovering hidden patterns or structures. Unsupervised learning is often used for clustering, dimensionality reduction, and anomaly detection. Here are the key algorithms in this particular category. We have divided again into two different categories. One, clustering algorithms. They are k-means clustering, hierarchical clustering, DB-scan or density-based spatial clustering of applications with noise, Gaussian mixture models or GMM, and we also have dimensionality reduction algorithms. These are principal component analysis or PCA, T distributed stochastic neighbor embedding or TSNE, and autoencoders. So these are the unsupervised learning algorithms which we will be learning about implementation. Next, we have other specialized categories. Now, let's talk about some other specialized machine learning algorithms that don't fit strictly into the supervised or unsupervised categories. These algorithms are designed for specific types of tasks or data. The ones that we will be looking are divided into four categories. First one is semi-supervised learning, and we will be looking at self-training. We have reinforcement learning, where we will be learning about Q learning, deep Q networks or DQN, policy gradient methods, and then we have anomaly detection algorithms, under which we will learn one class SVM, isolation forest, and finally we have the neural networks, which is deep learning, and here we will look at convolutional neural networks or CNNs, recurrent neural networks RNNs, long short term memory LSTM, and transformers. And that's it. Here we will cover a comprehensive list of essential machine learning algorithms that an AI engineer should know, organized into supervised, unsupervised, and specialized categories. Now, each of these algorithms has its strengths and ideal use cases, from basic prediction to handling complex high dimensional data. So let's get started into implementation of these algorithms. Linear regression. Now, linear regression is a supervised learning algorithm used for predicting a continuous target variable based on one or more input features. It finds the line of best fit, which is also called as linear relationship, by minimizing the sum of squared differences between the actual and predicted values. Let's see how we can implement or have a simple implementation using scikit-learn in Python. So I'm going to open my code editor. I've already created a file called as linear regression.py, and I'm going to go one step at a time. So let's start with importing necessary libraries. So I need first from sklearn.linear model import linear regression. This imports the linear regression class from scikit-learn's linear model module. This class is used to create a linear regression model for predicting continuous target values. Next, from sklearn.model selection, import train test split. This imports the train test split function, which is used to split the data set into training and testing sets, helping evaluate the model's performance on unseen data. Next, from sklearn.metrics, import mean squared error. This imports the mean squared error function, which calculates the mean squared error MSE between actual and predicted values. MSE is commonly used to evaluate regression models where lower values indicate better performance. Next, import numpy as NP. This imports the numpy library, which is a fundamental library for numerical computations in Python. It's commonly abbreviated as NP. Next, let's get some sample data. In this particular case, we can get house size versus house price. So I'm going to create an array x equal to np array and give some numbers inside it. If you look at it, this is based on the house sizes in square meters. So this defines the feature data x as a numpy array where each element is a list containing a single number representing house size in square feet. The shape of x is 10, 1, meaning there are 10 example rows with one feature column. Next, let's do for y, and this is y equal to np.array, and I've added some values which are house prices. This defines the target data y as a numpy array containing house prices. Each value in y represents the price corresponding to house size in x. So that's what this is. Now, next step is to split the data into training and testing sets. This can be done using that function that we imported, which is train test split. And in here, this line kind of splits the data into training and testing sets, where we get x train and y train, which are the training data which the model uses to learn. And then we also have x test and y test, the testing data, which is used to evaluate the model's performance. We have specified the test size as 0.2, which specifies that 20% of the data should be used for testing and the remaining 80% for training. We've given a random state of 42. Now, this sets a random seed for reproducibility. The seed ensures that each time you run this code, the same split of training and testing data is generated. Next step is to initialize the training model. We can do that by saying model equal to linear regression. This creates an instance of the linear regression class, which represents a simple linear regression model. Then we're going to fit the model. So fit the data into the model. This trains the model on the training data x train and y train. During this process, the model learns the relationship between house size and price by finding the best fit line that minimizes the error in predicting y train from x train. Now, using this, let's make predictions. So to make predictions, I'm going to say ypred equal to model.predict x test. Now this generates predictions for the testing set x test. The predict method uses the trained model to output estimated house prices, which are ypred, for the house sizes in x test. So once this is done, let's go ahead and evaluate the model. To evaluate the model, we'll use MSE, where MSE is mean squared error y test, ypred. Now, this calculates the mean squared error MSE between the actual values y test and the predicted values ypred. MSE measures how well the model's predictions match the true values, with lower values indicating better performance. Next, let's go ahead and print these out. Print the mean square error and print the predicted values. Together, this code demonstrates a full workflow for training and evaluating a simple linear regression model in Python, from data preparation and data training to prediction and performance evaluation. So let's go ahead and run this code. I'm going to open my terminal or command prompt. Here, make sure we have that file. We are in the right path. I'm going to say Python linear regression.py. And there you go. We have the mean squared error of some big number and predicted values of for two different houses. One is 235,000 and the other one is 257,000. These are the predicted values. I hope you were able to follow along and understand this. If you have any questions or comments, let me know and I'll get back to you. Ridge and lasso regression. Ridge and lasso regression are regularization techniques applied to linear regression to prevent overfitting by penalizing large coefficients. Ridge regression adds an L2 penalty, which is sum of squared coefficients, whereas lasso regression adds an L1 penalty, which is sum of absolute values of coefficients, which can lead to feature selection by shrinking some coefficients to zero. Let's go and look at a simple implementation using scikit-learn for both ridge and lasso regression. I'm going to jump into my editor, and here we'll start with importing necessary libraries. First, from sklearn.linear model, import ridge and lasso. Now, this imports the ridge and lasso classes from scikit-learn's linear model module. Ridge and lasso are types of linear regression models with added regularization, which is penalty terms, to prevent overfitting. Ridge uses L2 regularization while lasso uses L1 regularization. Next, we will from sklearn.model selection import train test split. This imports the train test split function, which is used to divide the data set into training and testing sets. This helps evaluate how well the model generalizes to unseen data. Next, from sklearn.metrics, import mean square error. This imports the mean squared error function, which calculates the mean squared error or MSE between the actual and the predicted values. Now, MSE is a common metric for evaluating regression models. A lower value indicates a better fit. Finally, we'll import NumPy as NP. This imports the NumPy library, which provides support for working with arrays and numerical data. It is fundamental library for scientific computation in Python. Now let's go ahead and get the sample data. We're going to use the same sample data that we used in the previous project. So it's x equal to np array with the square feet and y equal to np array with the pricing. So x here defines the feature data x as a numpy array where each element is a list representing the size of the house in square feet. Here x has a shape of 10, 1, meaning there are 10 example rows with one feature. And then y equal to np dot array defines the target data y as a numpy array representing house prices corresponding to each item, each size in x. So these are all representations. Next step is to split the data into training and testing sets. This can be done using the train test split method. This splits the data into training and testing sets. We get x train and y train, which is used to train the model, and we get x test and y test used to test the model's performance. Now test size here is specified as 0.2, which specifies that 20% of data should be used for testing while 80% will be used for training. So in our case, since we have 10 records, it will be 8 and 2. Next, we have random state equal to 42, which sets the random seed for reproducibility, ensuring that the data split will be the same each time the code is run. So next step is let's jump into ridge regression. Now for this, first I'm going to say ridge model equal to ridge alpha 1.2. Now this initializes the ridge regression model. The alpha parameter controls the strength of the regularization, with higher values applying a stronger penalty to larger coefficients. And alpha of 1.2 is often a good starting point. Next, ridge model.fit x train y train. This trains the ridge model on the training data. The model learns the relationship between house size and price, fitting a line that minimizes error while applying the L2 regularization penalty. Next, we have ridge pred equal to ridge underscore model dot predict x test. This uses the trained ridge model to make predictions on the test set, which is x underscore test. The model outputs predicted prices based on house sizes in X test. Next, we have ridge MSE equal to mean squared error, and we'll pass Y test and ridge pred. This calculates the mean squared error MSE between the actual values Y test and the predicted values ridge pred. MSE provides a measure of the model's accuracy with lower values indicating better performance. Next, let's go ahead and print the ridge mean squared error. This prints the MSE for ridge regression, allowing you to assess how well the model performed on test data. Now next, let's go into lasso regression. So for this, I'm going to say lasso regression equal to lasso alpha 0.1, which initializes a lasso regression model. Here alpha controls the L1 regularization strength, with larger values increasing the penalty on the coefficients. Setting alpha equal to 0.1 applies a mild regularization. So let's go. Next step is lasso model dot fit x train y train. This trains the lasso model on the training data. Like ridge, the model learns the relationship between house size and price, but lasso may shrink some coefficients to zero, effectively selecting features and reducing complexity. Lasso pred equal to lasso model dot predict x test. This uses the trained lasso model to make predictions on the test set. The model outputs predicted prices based on the house sizes in X test. Next step is lasso MSE, mean squared error, and we pass Y test and lasso pred. This calculates the mean squared error between the actual prices Y test and the predicted prices lasso pred. MSE indicates the accuracy of the lasso model with lower values representing a better fit. Next, finally, we'll print the lasso. This will print the MSE for the lasso regression model, allowing you to compare its performance with the ridge model. Now, this code here provides a practical example of implementing ridge and lasso regression for predicting house prices and comparing their mean square error to understand the impact of regularization on model performance. So let's go ahead and run this project. I'm going to say Python ridge lasso regression py, run it, and it will give me the ridge mean square error is this much and the lasso mean square error is this much. So you can compare these two numbers. I mean, with the data set that we have, since we have only 10 fields, it might not be the best, but if you have a bigger data set, it will give you a better idea of which one to use, either ridge or lasso or maybe both. So I hope this helped. And if you have any questions on implementing or had any issues, let me know in the comments and I'll get back to you. Polynomial regression. Polynomial regression is an extension of linear regression that models the relationship between the input features and the target variable as an nth degree polynomial. It can capture non-linear relationships in the data by adding polynomial terms to the features. Now let's go and implement this. Here's a line-by-line breakdown of the code for implementing polynomial regression in Python. I've created a file called as polynomialregression.py, and let's go over one line at a time. First, let's import the necessary libraries. We're going to import sklearn.linearModel import linear regression, which imports the linear regression class from scikit-learn, which we'll use to create a linear regression model for polynomial regression. This model will fit a line to the transformed polynomial features. Next, from sklearn preprocessing, import polynomial features. This imports the polynomial features class, which is used to generate polynomial features of a specified degree. This transformation allows the linear regression model to fit a non-linear relationship by adding polynomial terms. Next, from sklearn model selection, import train test split. This imports the train test split function to split the dataset into training and testing sets, enabling evaluation of the model's performance on unseen data. Next, from sklearn.metrics, import mean squared error. This imports the mean squared error function to evaluate the model by calculating the mean squared error or MSE between actual and predicted values. Lower MSE indicates better performance. Next, we will import NumPy as NP. This imports the NumPy library for creating arrays and performing numerical operations in Python. Let's start with the sample data. In this particular example, I'm going to use experience versus salary. So for my experience, I'm going to say depending on how many years of experience you have, 1, 2, 3, 4, 5. So this X defines the feature data X as a NumPy array where each value represents the years of experience. The shape of X is 10, 1, meaning it has 10 examples with one feature each. Next, I have y equal to np array, and I have the salaries over here, which defines the target data of y as a numpy array where each value represents the corresponding salary. The relationship between experience and salary is nonlinear, making it suitable for polynomial regression. Let's split the data into training and testing sets. For that, I'm going to use the same train test split, which splits the data into training and testing sets. We get xtrain and ytrain used to train the model, and xtest and ytest used to test the model's performance. The test size is specified as 0.2, which means that 20% of the data will be used for testing, with the remaining 80% for training. A random state is set to 42, which sets a seed for reproducibility, ensuring the same split each time the code is run. Now let's go ahead and transform features into polynomial features. This can be done using first poly equal to polynomial features degree of 2. Now this initializes a polynomial feature object with degree 2. This means we'll transform the feature x into a second degree polynomial, adding squared terms to represent the nonlinear relationship. Next, I'm going to say xtrain poly equal to poly dot fit transform xtrain, which transforms the xtrain data into a polynomial features. For degree 2, this transformation will add an additional column representing x square alongside the original feature, allowing a linear regression model to fit a quadratic curve. Next, I'll say xtest poly equal to poly dot transform xtest. This transforms the xtest data into polynomial features using the same transformation. We only call transform, not fit transform, to ensure consistency with the training data transformation. Next, let's go ahead and initialize and train the model. To initialize the model, I will say model equal to linear regression. This initializes a linear regression model. This model will fit a linear relationship to polynomial transform data. Next, I am going to say fit xtrain poly ytrain. This trains the model on the polynomial transformed training data xtrain poly and target values ytrain. The model learns the relationship between the experience in polynomial form and salary, allowing it to capture non-linear patterns. Next, let's say make some predictions. I'm going to move this up so we can see clearly. Ypred equal to model.predict x test poly. This uses the trained model to make predictions on the test set x test poly. These predictions are based on the polynomial features of x test, allowing the model to output salary estimates based on years of experience. Next, let's evaluate the model. So first, we'll do MSE, mean squared error, ytest, ypred. This calculates the mean squared error between the actual values ytest and the predicted values ypred. MSE provides a measure of the model's accuracy, with lower values indicating a better fit. Next, let's print the mean squared error. This prints the calculated MSE to evaluate how well the model performs on the test data. And this prints the predicted salary values for each test sample, allowing us to compare them against the actual y-test values. Now this code here demonstrates how to use a polynomial regression to fit a non-linear relationship between years of experience and salary. By transforming the features into polynomial terms, we allow a simple linear regression model to fit a curve to the data. So let's go ahead and run this example. I'm going to open terminal. Python polynomial regression.py, and it will give me the mean squared error and the predicted values for the salaries right here. So I hope you were able to follow along in implementing polynomial regression. And if you have any questions or comments, let me know in the comments and I'll get back to you. Logistic regression. Logistic regression is a supervised learning algorithm used for binary classification problems. Example, yes, no, spam or not spam. Instead of predicting a continuous output, it predicts the probability of an observation belonging to a particular class by applying the logistic, which is the sigmoid function, which outputs values between 0 and 1. So let's go ahead and write code for this. Here is the line by line breakdown of the code for implementing logistic regression in Python. So first step, I'm going to go and import the necessary libraries. Now from sklearn.linear model import logistic regression, this imports the logistic regression class from scikit-learn, which is used to create a logistic regression model. Now, the logistic regression is typically used for binary classification tasks, as I mentioned, where the goal is to predict one of the two possible outcomes. Next, from sklearn.model prediction, import train test split. This imports the train test split function, which splits the dataset into training and testing sets. This allows us to evaluate how well the model generalizes to unseen data. Next, from sklearn metrics, import accuracy score and confusion matrix. This imports accuracy score, which calculates the accuracy of predictions, and confusion matrix, which provides detailed insights into the model's classification performance, showing the true positives, true negatives, false positives, and false negatives. Next, we'll import NumPy as NP. This imports the NumPy library, which is fundamental for numerical computations in Python, especially for creating and manipulating arrays. So now let's go ahead and create those sample data. We have our studies versus pass and fail. So first is x equal to np array, and I've mentioned how many hours you studied, which defines the feature data x as a NumPy array, where each element is a list representing hours studied by a student. Here the shape of x is 10, 1, indicating 10 examples or rows with one feature, which is the column. Next, I have y equal to np array. It defines the target data y as a NumPy array containing the outcomes of the study hours, where 0 represents fail and 1 represents pass. Now this is binary classification task, making it well suited for logistic regression. So let's go ahead and next split the data into training and testing sets. I can do that by calling that train test split function, which splits the data into training and testing sets. We have xtrain and ytrain, which is used for training the model, and we have xtest and ytest, which is used to test the model's performance. The test size is specified as 0.2, which specifies that 20% of the data should be used for testing, while the remaining 80% will be used for training. Our random state is 42, which sets a seed for reproducibility, ensuring that each time the code is run, the same data split is generated. Now let's go ahead and initialize and train the model. To do that, I am going to start with model equal to logistic regression. This initializes the logistic regression model. Now the logistic regression will find the best fitting logistic or S-shaped curve that separates the binary outcomes. I'm going to go ahead and say model.fit and pass xtrain and ytrain, which trains the logistic regression model on the training data xtrain and ytrain. The model learns the relationship between hours studied and the pass-fail outcome, estimating parameters that allow it to predict binary outcomes. Now let's go and make predictions. Ypred equal to model predict xtest. This uses the trained logistic regression model to make predictions on the test data xtest. The output ypred contains the model's predictions, where each value is either 0 fail or 1 pass, corresponding to the model's estimate of whether a student passed or failed based on hours studied. Now let's go ahead and evaluate this model. I'm going to use accuracy score, ytest, ypred. This calculates the accuracy of the model by comparing the actual values ytest to predicted values ypred. Accuracy is the ratio of correctly predicted instances to the total instances. Next, confusion matrix equal to confusion matrix ytest ypred. This computes the confusion matrix for the model, showing a breakdown of true positives, true negatives, false positives, and false negatives. This helps to understand the model's classification performance in more detail. Next, we print the accuracy and we'll print the confusion matrix to check the results. So this code provides a complete example of a logistic regression workflow, including data preparation, model training, prediction, and performance evaluation. This is particularly useful for binary classification tasks where the goal is to predict one of the two outcomes, in this case, fail versus pass. So let's go ahead and run this project. I'm going to save it, go here and say Python logistic regression. And there you go. Our accuracy is 1.0. Confusion matrix with true positives, true negatives, false positives, and false negatives is displayed right here. I hope you were able to follow along and implement this. If you have any problems, questions, let me know in the comments and I'll get back to you. K nearest neighbors, or KNN, is a simple non-parametric classification or regression algorithm. It classifies new data points based on the majority class of the k nearest points in the feature space. It's particularly useful for smaller data sets where the relationship among data points can be easily visualized. Let's go ahead and implement a line-by-line code for implementing k nearest neighbors in Python. So first, let's go ahead and import the necessary libraries. First, we'll need from sklearn.neighbors import kneighbors classifier, which imports the kneighbors classifier class from scikit-learn's neighbors module. This class implements the k-nearest neighbors algorithm for classification tasks, where the model classifies data points based on classes of the nearest data points. Next, from sklearn.model-selection, import the train test split. This imports the train test split function, which is used to divide the dataset into training and testing sets. This helps in evaluating how well the model generalizes the new data. Next, we have from sklearn.metrics import accuracy score and confusion matrix. This imports the accuracy score for measuring the overall accuracy of predictions and confusion metrics for a detailed breakdown of the model's performance, showing counts of true positives, true negatives, false positives, and false negatives. And then finally, we'll import numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulation in Python. Next, let's get the sample data. Here we are using hours studied and prior grades versus pass fail. So we have the x equal to np array, which defines the feature data x as a numpy array where each sublist contains two values. First value represents hours studied by a student. The second value represents prior grades, example percentage. Now x has the shape of 10, 2, indicating that 10 examples with 2 features each. Next, we have y equal to np array. This defines the target data y as a numpy array containing binary outcomes. 0 for fail and 1 represents pass. This is a binary classification task where we aim to predict whether a student will pass or fail based on their study hours and prior grades. So let's go ahead and split the data into training and testing sets. We can do that using train test split function. This splits the data into training and testing sets. We get xtrain and ytrain used to train the model, and xtest and ytest, which is used to test the model's performance. Our test size, as usual, is specified that 20% of the data will be used for testing, while the remaining 80% will be used for training. A random state equal to 42, which sets a seed for reproducibility, ensuring that each time the code is run, the data is split in the same way. Next, go ahead and initialize and train the model with the K3. So to do that, I can specify model k neighbors classifier n neighbors equal to 3, that initializes a k nearest neighbors KNN classifier model with k equal to 3, meaning the model will classify a new data point based on a majority class among its 3 nearest neighbors. You can increase it, reduce it, up to you. Next, we have model.fit xtrain ytrain. This trains the KNN model on the training data xtrain and ytrain. KNN is non-parametric model, meaning it doesn't learn a specific set of parameters. Instead, it stores the training data to make predictions based on the nearest neighbors. Next, go ahead and make predictions. So I will use ypred model.predict xtest. Uses the trained KNN model to make predictions on the test set xtest. The model classifies each data point in xtest based on the majority class of its 3 nearest neighbors as specified by n neighbors equal to 3. The output ypred contains the predicted classes, which is 0 or 1, for each data point in the test set. Next, let's go ahead and evaluate the model. Accuracy equal underscore score ytest ypred. This calculates the accuracy of the model by comparing the actual values ytest to the predicted values ypred. Accuracy is the ratio of correctly predicted instances to the total instances in the test set. Next, we're going to do the confusion matrix, and this computes the confusion matrix for the model, showing a breakdown of true positives, true negatives, false positives, and false negatives. This helps to understand the model's classification performance in greater detail. Let's go ahead and print the accuracy out and then print the confusion matrix out. Now, this code demonstrates a full workflow for training and evaluating a k nearest neighbor classifier. The KNN model predicts binary outcomes based on our studied and prior grades, showing how it classifies each test data point by looking at the classes of the nearest neighbors. Let's go ahead and run it. Open my terminal, say Python k nearest neighbor, run it, and we'll get the output of accuracy and the confusion matrix here. Now, if you have any problems or had any issues or have any questions about this, let me know and I'll get back to you. Support vector machines, or SVM. Support vector machines is a powerful classification algorithm that works by finding the hyperplane that best separates classes in the feature space. SVM aims to maximize the margin between the classes, making it a good choice for binary classification, especially when the classes are well separated. Let's go line by line breakdown of the code for implementing support vector machines for classification in Python. So I created an empty file first. Here, first step, as usual, is to import necessary libraries. So I'm going to import sklearn.svm and import from there svc. This imports the svc class, the support vector classifier, from sklearn's svm module. svc is used for classification tasks and aims to find the optimal hyperplane that separates classes in the feature space. Next, we'll from sklearn.model_selection import train test split. This imports the train test split function to divide the data set into training and testing sets, which helps in evaluating the model's generalizability to new data. Next, from sklearn metrics, import accuracy score and confusion matrix. This imports accuracy score to measure the accuracy of the predictions and confusion matrix to provide a breakdown of the model's classification performance, showing counts of true positive, true negative, false positive, and false negative. Next, import numpy as np. This imports the numpy library, which is widely used for numerical operations and array manipulation in Python. The next step is to get the sample data. Here we have our studied and grades versus pass fail. So we'll do x equal to np array, and I have added some data here which defines the feature data x as a numpy array. Each sublist represents a data point with two features. The first value represents hours studied by a student. The second value represents prior grades, example percentages. The shape of x is 10, 2, indicating 10 example rows with two features each. Next, I'm going to get the y equal to np array, which defines the target data y as a numpy array containing binary class labels. 0 represents fail and 1 represents pass. This is a binary classification task now suitable for SVM. So let's go ahead and split the data into training and testing sets. We can do that by calling the train test split method. Here we have the train test split method, which splits the data into training and testing sets. Now xtrain and ytrain are used to train the model, whereas xtest and ytest are used to test the model's performance. Also, we have specified test size is 0.2, which means that 20% of the data will be used for testing while 80% is used for training. We're giving a random state of 42, which sets a seed for reproducibility, ensuring that the data is split is same each time the code is run. Next, let's go ahead and initialize and train the model. To initialize the model, I'll say model equal to svc kernel equal to linear. Now this initializes an SVM classifier with a linear kernel. The kernel equal to linear argument specifies that we want to use a linear SVM, which attempts to find a linear hyperplane that best separates the two classes. Other kernel options such as RBF or poly are available for non-linear classification, but here we are going to use linear. Next, we'll do fitting. We'll say model fit xtrain ytrain. Now this trains the SVM model on the training data xtrain and ytrain. The model learns and the optimal hyperplane that separates the data points belonging to each class, maximizing the margin between them. Next, let's make some predictions. Ypred equal to model.predict xtest. This uses the trained SVM model to make predictions on the test set xtest. For each data point in xtest, the model predicts either 0, which is fail, or 1, which is pass, based on which side of the hyperplane the data point falls. Next one is to evaluate the model. Now here, we'll first use the accuracy and then the confusion matrix. So the accuracy equal to accuracy score ytest ypred calculates the accuracy of the model by comparing the actual values, which is the ytest, to the predicted values ypred. Accuracy is the ratio of correctly predicted instances to the total instances in the test set. Next, a confusion matrix, which computes the confusion matrix for the model, showing a breakdown of true positives, which are correctly predicted passes, true negatives, which are correctly predicted fails, then we have false positives, which are incorrectly predicted passes, and we have false negatives, which are incorrectly predicted fails. Now this provides a more detailed view of the model's performance. And next steps, just go ahead and print the accuracy and the confusion matrix. So this code here demonstrates a complete implementation of the support vector machine classifier, showing how it uses our studied and prior grades to classify students as passing or failing. The SVM model is trained, tested, and evaluated using both accuracy and a confusion matrix. So I hope you were able to follow along. I'm going to run this right now. Let's say first make sure I save it, and I'm going to say Python support and run it. It will give me the accuracy and the confusion matrix. So it's pretty good, and I hope you were able to follow along. If you have any questions or comments, let me know and I'll get back to you. Decision trees. Decision trees are a versatile supervised learning algorithm used for both classification and regression. They work by recursively splitting the data into subsets based on the feature that provides the most information gain. Each node represents a decision based on a feature, and each leaf node represents a prediction. Let's go line by line breakdown of the code for implementing a decision tree classifier in Python. I have already created the basic file. I'm going to run through the first few commands, which is first import the necessary libraries. Now for this, we are going to call from sklearn.tree import decision tree classifier, which imports the decision tree classifier class from scikit-learn's tree module. This class is used to create a decision tree model, which makes predictions by learning simple decision rules from data features. Next, from sklearn.model selection, import train test split. This imports the train test split function, which is used to split the dataset into training and testing sets. This allows the model to be trained on one subset of the data and evaluated on another. Next, from sklearn.metrics, import accuracy score and confusion metrics. This imports accuracy score to measure the model's prediction accuracy and confusion metrics to evaluate performance by counting the correct and incorrect predictions for each class. Import NumPy as NP. This imports the NumPy library, a popular package for numerical operations and array manipulation in Python. Let's get to sample data. The sample data is again same as before, hours studied and grades versus pass fail. So I'm going to create an X array, which is np.array, which defines the feature data X as numpy array, where each element contains two values. The first value represents hours studied by a student. The second value represents prior grades. Example, the percentage. The shape of X is 10, 2, indicating 10 example rows with two feature columns. Next, y equal to np array, which defines the target data y as numpy array containing binary outcomes. 0 represents fail and 1 represents pass. This is a binary classification task which is ideal for a decision tree classifier. Next step, let's split the data into training and testing sets. We call xtrain, xtest, ytrain, ytest, and call the train test split function, which splits the data into training and testing sets. Now, xtrain and ytrain used to train the model, whereas xtest and ytest is used to evaluate the model's performance. The test size is 0.2, specifies that 20% of the data should be used for testing and the remaining 80% should be used for training. The random state is 42, which sets a seed for reproducibility, ensuring that each time the code is run, the data split is the same. Next, let's go and initialize and train the model. First, model equal to decision tree classifier. This initializes a decision tree classifier model. By default, the classifier will split data based on the Gini impurity metric to decide the best splits at each node. Other splitting criteria such as entropy are available, but this is what we're going to use right now. Next, model.fit xtrain ytrain. Trains the decision tree model on the training data x underscore train and y underscore train. During this process, the model learns the relationship between features, hours studied, and grades, and the target variable pass fail, building a tree structure with decision nodes that allows it to classify the new data. Next, let's go ahead and make predictions. Ypred equal to model.predict xtest. This uses the trained decision tree model to make predictions on the test set xtest. For each data point in xtest, the model predicts either 0 for fail or 1 for pass based on the decision rules it learned during training. Next, let's go ahead and evaluate the model based on accuracy score ytest ypred, which calculates the accuracy of the model by comparing the actual values ytest to the predicted values ypred. Accuracy is the ratio of correctly predicted instances to the total instances in the test set. Next, we're going to get the confusion metrics by calling the confusion metrics function, which computes the confusion metrics for the model, which provides a detailed view of the model's classification performance. We have true positives, which correctly predicted passes. We have true negatives with correctly predicted fails, false positives with incorrectly predicted passes, and false negative shows incorrectly predicted fails. Now, next is to print the accuracy and the confusion metrics to us to show us how it looks like. Now, this code provides a complete workflow for training and evaluating a decision tree classifier on data representing hours studied and prior grades. The decision tree model predicts whether a student will pass or fail based on the input data, and the evaluation metrics, which are accuracy and confusion metrics, provide insights into its performance. Let's go ahead and run this code. Let's say Python decision tree, And there you go, we have the accuracy and the confusion metrics for this. So that's perfect. And I hope you were able to follow along and build this application. If not, let me know if you had any issues or any problems or any want to tell me something about the project. Go ahead and leave them in the comments and I'll get back to you. Random forest. Now, random forests are an ensembled learning method that combines multiple decision trees to make a more accurate and stable prediction. Each tree in the forest is trained on a random subset of the data, and the final prediction is made by averaging for regression or voting for classification the predictions of individual trees. This helps to reduce overfitting and improve generalization. Now let's go ahead and implement step by step and break down the code for implementing a random forest classifier in Python. So first, I'm going to go ahead and import the necessary libraries. We're going to get our sklearn ensemble import random forest classifier, which imports the random forest classifier class from scikit-learn's ensemble module. Now, the random forest classifier is an ensemble learning method that builds multiple decision trees and combines their outputs to improve accuracy and reduce overfitting. From sklearn.model selection, we import train test split. This imports the train test split function, which splits the dataset into training and testing sets, allowing for model evaluation on unseen data. Next, from sklearn.metrics, we import accuracy score confusion metrics, which imports the accuracy score to calculate the accuracy of the model and confusion metrics to provide a detailed breakdown of the model's prediction, showing the counts of true positive, true negatives, false positives, and false negatives. Next, we import numpy as np. This imports the numpy library, a popular package for numerical computation and array manipulation in Python. Now next, let's get the sample data. Again, we're going to use the same data, which is hours studied and grades versus pass-fail. So here it is x equal to np array, which defines the feature data x as a numpy array, each element in the list representing two features for each subset. First one, the first value represents the hours studied, the second value represents prior grades, which is in percentages. The shape of x is 10,2, meaning it has 10 example rows with two feature columns. Y equal to np.array, and this defines the target data y as a numpy array containing binary outcomes. 0 represents fail and 1 represents pass. This is a binary classification task, making it suitable for a random forest classifier. So let's go ahead and split the data into training and testing sets. We call this train test split function, which splits the data into training and testing sets. Xtrain and Ytrain are used to train the model, and Xtest and Ytest are used to evaluate the model's performance. Text size of 0.2 specifies that 20% of the data should be used for testing and the remaining 80% should be used for training. The random state of 42 sets a seed for reproducibility, ensuring that the data split remains the same each time the code is run. Let's go ahead and initialize and train the model. For that, we'll say model equal to random forest classifier, and we pass n estimators 100 and random state 42. Now here it initializes the random forest classifier with the following parameters. N estimators 100 specifies the number of decision trees in the forest. The model builds 100 decision trees, each trained on random subsets of data. A higher number of trees generally increases accuracy, but it also requires more computation. Random state equal to 42 ensures reproducibility, meaning each run will produce the same results. Next, we're going to do model.fit xtrain ytrain. This trains the random forest model on the training data xtrain and ytrain. The model creates an ensemble of decision trees that learn the relationship between features, which is hours studied and grades in our case, and the target variable pass and fail. Now let's go ahead and make predictions. We can do that by ypred model predict xtest, which uses the trained random forest model to make predictions on the test set xtest for each data point in xtest. The model predicts either 0 for fail or 1 for pass based on the majority vote from all the trees in the forest. Now next, let's go ahead and evaluate the model. Here, we're going to use accuracy equal to accuracy score, uh, which calculates the accuracy of the model by comparing the actual values y test to the predicted value y pred. Accuracy is the ratio of correctly predicted instances to the total instances in the test set. Next, we have the confusion matrix, which compute the confusion matrix for the model, showing the true positives, true negatives, false positives, and false negatives. Finally, let's go ahead and print the accuracy and the confusion matrix. So this code here demonstrates a complete workflow for training and evaluating a random forest classifier, which predicts whether a student will pass or fail based on the hours studied and grades. The model is evaluated using both accuracy and confusion matrix, offering a detailed assessment of its performance. Let's run this, save it first, go ahead and say Python random forests.py, and there you go, we have the accuracy and confusion matrix. And if you were able to follow along, that's good. If not, if you have any questions or any problems, let me know and I'll get back to you. Gradient boosting. Gradient boosting is an ensemble technique that builds a series of decision trees where each tree corrects the errors of the previous ones. By combining the predictions of these trees, gradient boosting models create a more accurate final prediction. Popular implementations include XGBoost, LightGBM, and CatBoost, which are optimized for speed and accuracy. Let's go ahead, write the code for this implementation line by line with explaining each and every line of code implementing a gradient boosting classifier in Python. So let's get started. I'm going to open a new file and here start with importing the necessary libraries. From sklearn ensemble import gradient boosting classifier, which imports the gradient boosting classifier class from scikit-learn's ensemble module. Gradient boosting is an ensemble method that builds multiple weak learners, typically decision trees, sequentially, where each tree tries to correct the errors of the previous ones. Now from sklearn.model selection, we import train test split. This imports the train test split function, which splits the dataset into training and testing sets, allowing for model evaluation on unseen data. Next, from sklearn.metrics, import accuracy score and confusion metrics, which imports the accuracy score to calculate the accuracy of the model and confusion metrics to provide a breakdown of the model's predictions, displaying the counts of true positives, true negatives, false positives, and false negatives. Next, we'll import numpy as np. This imports the numpy library, which provides support for numerical computations and array manipulations in Python. Now let's get some sample data. Same as before, we're going to use the hours studied and grades versus pass fail. We created an x equal to np array, which defines the feature data x as numpy array. Each element contains two values. The first value represents hours studied by a student. The second value represents prior grades in percentage. The shape of x is 10, 2, meaning it has 10 example rows with two features as columns. Next, we're going to do y equal to np array. This defines the target data y as a numpy array containing binary outcomes. 0 represents fail and 1 represents pass. Now this is a binary classification task ideal for gradient boosting model. Now let's go and split the data into training and test sets. So this can be done using the train test split function, which splits the data into training and testing sets. Xtrain and ytrain are used to train the model. Xtest and ytest are used to evaluate the model's performance. Also, we have the test size of 0.2, which specifies that 20% of the data should be used for testing, with the remaining 80% used for training. A random state is set to 42, sets a seed for reproducibility, ensuring that the same data split is generated each time the code is run. Now let's go ahead and initialize and train the model. So first, model equal to gradient boosting classifier with n estimators as 100, learning rate is 0.1, and random state equal to 42. This kind of initializes a gradient boosting classifier model with the parameters n equal estimators equal to 100, which specifies the number of boosting stages, which are trees, in the ensemble. A higher value generally improves accuracy but increases computation time. The learning rate of zero point 0.1 controls the contribution of each tree to the final prediction. A smaller learning rate requires more trees, but it can lead to better generalization. And random state equal to 42 ensures reproducibility by setting a random seed. Next, let's go ahead and fit the model with X train and Y train. This trains the gradient boosting model on the training data X train and Y train. The model builds a series of weak learners, each one improving upon the errors of the previous one, creating a more accurate overall model. Now let's make predictions. It's a ypred equal to model predict X test. What it does is it uses the trained gradient boosting model to make predictions on the test set, which is X test. For each data point in X test, the model predicts either 0, which is fail, or 1, which is pass, based on the learned patterns. Now let's go ahead and evaluate the model. To evaluate the model, we'll use accuracy score, which calculates the accuracy of the model by comparing the actual values, y test, to the predicted values, ypred. Accuracy is the ratio of correctly predicted instances to the total instances in the set. Next, let's get the confusion matrix by calling confusion matrix function, which computes the confusion matrix for the model, providing a breakdown of true positives, true negatives, false positives, and false negatives. And then finally, let's go ahead and print the accuracy and the confusion matrix. So now this code demonstrates the use of a gradient boosting classifier to predict whether a student will pass or fail based on the hours studied and the grades. The model's performance is evaluated using accuracy and confusion metrics here, providing a comprehensive view of its classification results. Let's go ahead, save this file, and run it here. I'm going to clear the previous one and say Python gradient boosting. And we have the accuracy and the confusion matrix with the true positives, true negatives, false positives, and false negatives. It looks pretty much perfect. So if you were able to do this along with me, that's great. If you have any questions or problems or comments, let me know and I'll get back to you. Naive Bayes. Naive Bayes is a probabilistic classifier based on Bayes' theorem, which assumes that the features are conditionally independent given the class label. Despite this naive assumption, it often performs well in text classification and spam detection tasks. Let's go ahead line by line in writing the code for implementing a naive Bayes classifier using the Gaussian naive Bayes algorithm in Python. I'm going to start with a new file, empty file here. We're going to start by saying import the necessary libraries. From sklearn naive Bayes import Gaussian NB, which imports the Gaussian NB class from scikit-learn's naive Bayes module. Now, Gaussian naive Bayes is a probabilistic classifier based on Bayes' theorem, assuming that each feature follows a Gaussian, which is normal distribution. It is particularly used for continuous data. Next, we're going to do sklearn.model selection import train test split. This imports the train test split function, which splits the data set into training and testing sets, allowing for model evaluation on unseen data. Next, from sklearn model or metrics, import accuracy store and confusion metrics, which imports the accuracy score to calculate the model's prediction accuracy, and confusion metrics to evaluate the model by showing counts of true positives, true negatives, false positives, and false negative. Next, let's import numpy as np, which imports the numpy library, which provides support for numerical computations and array manipulation in Python. Let's go ahead and pick up our sample data, which is same as the previous project, hours studied and grades versus pass file. So we have x equal to np array, which defines the feature data x as a numpy array where each element contains two values. The first value represents hours studied by a student. The second value represents prior grades, which are percentages. The shape of x is 10,2, meaning there are 10 examples rows with two features which are columns. Y is equal to np array, which defines the target data y as a numpy array containing binary outcomes. 0 represents fail and 1 represents pass. This is a binary classification task, which is, in our case, ideal for Gaussian naive Bayes classifier. So let's go ahead and split the data into training and testing sets. So we'll write the code for that, which is same as before. Nothing has changed here. What it does is it splits the data into into training and testing sets. X train and Y train are used to train the model. X test and Y test are used to evaluate the model's performance. The test size is 0.2, which specifies that 20% of the data should be used for testing, while the remaining 80% used for training. Now random state equal to 42, which sets a seed for reproducibility, ensuring that each time the code is run, the same data split is generated. Next, let's go and initialize and train the model. Model equal to Gaussian NB. This initializes the Gaussian naive Bayes classifier. This classifier will assume each feature is normally distributed and will calculate probabilities based on this assumption. You're going to say model.fit x train y train. This trains the Gaussian naive Bayes model on the training data x train and y train. During training, the model calculates the mean and variance of each feature and each class pass fail to define the Gaussian distribution used for prediction. Now, using that, let's make the predictions. We use the model and say predict. This uses the trained Gaussian naive Bayes model to make predictions on the test set X test. For each data point in X test, the model predicts either 0, which is for fail, or 1 for pass, based on the highest calculated probability for each class. Next, let's go and evaluate the model. To evaluate the model, I'm going to use the accuracy score and the confusion matrix. The accuracy score calculates the accuracy of the model by comparing the actual values y test to predicted values y pred. Accuracy is the ratio of correctly predicted instances to the total instances in the test set. Confusion matrix, on the other hand, computes the confusion matrix for the model, which provides a breakdown of true positives, which are correctly predicted passes, true negatives, which are correctly predicted fails, false positives, which are incorrectly predicted passes, and false negatives, which are incorrectly predicted fails. Next, we'll go ahead and print accuracy and print the confusion matrix. So this code demonstrates a full workflow for using Gaussian naive Bayes to classify students as passing or failing based on hours studied and grades. The model is evaluated using both accuracy and a confusion matrix, providing a comprehensive view of its classification performance. Let's go ahead and run this. I'm going to open terminal, clear the previous one, and say Python naive Bayes, and it will give me accuracy and the confusion matrix. That's perfect. Again, if you had any problems following along or implementing this, let me know. If you have any comments or questions, let me know too, and I'll get back to you. K-means clustering. K-means clustering is an unsupervised learning algorithm that partitions data into K clusters. Each cluster is defined by its centroid, and each data point is assigned to the nearest cluster. The algorithm iteratively adjusts centroids to minimize the variance with each cluster. Let's jump into the implementation where we will write the code and explain line by line for implementing k-means clustering in Python. So I'm going to go here. I already have the file ready, and I'm going to first do is import the necessary libraries, which is from sklearn cluster import k-means. Now this imports the k-means class from scikit-learn's cluster module. K-means is a clustering algorithm that partitions data into a specified number of clusters by iteratively updating centroids until the clusters stabilize. Next, we'll import the numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulation in Python. Now let's get the sample data. Example, we'll get some points in 2D space, and that's what I have here, where x equal to np array defines the features data x as a numpy array where each sublist represents a data point in 2D space. Now each data point has two values, x and y coordinates. For example, 1, 2 and 10, 2 represent 2 points in the 2D plane. The shape of x is 6, 2, indicating 6 data points with 2 features each. Now let's go and initialize and fit the model. So initialize, I'll say k-means equal to k-means, n clusters equal to 2, random state equal to 42. Now this initializes a k-means clustering model with the following parameters of n clusters equal to 2. It specifies the data should be partitioned into 2 clusters, and random state 42 sets a random seed for reproducibility, ensuring the initial positions of the centroids are the same each time the code is run. Next, I'm going to say k-means fit x. Now fits the k-means model to the data x. During this process, the algorithm assigns data points to clusters by iteratively updating the positions of the centroids until convergence. Each point is assigned to the nearest centroid. Next, let's get the cluster centers and labels. To do that, I'm going to say centroids equal to k-means dot cluster underscore centers underscore. Now this retrieves the coordinates of the cluster centers, which are the centroids, after training. Each centroid represents the mean position of the points within a cluster in 2D space. Next, I'll say labels equal to k-means dot labels underscore. Now this retrieves the labels assigned to each data point in X, where each label represents the cluster 0 or 1 to which the point belongs. The labels allow you to see which points are grouped together. Next, let's go ahead and print the cluster centers, the centroids, and labels, which are the labels. And so this code kind of demonstrates how to use k-means clustering to group data points in 2D space into two clusters. After fitting the model, it outputs the centroids of each cluster and the assigned cluster labels for each data point, showing which points belong to which cluster. Let's run it and see. And there you go. We have our cluster centers 1 point, 2 point, and 10 and 2. And then the labels are 0, 0, 0 and 1, 1, 1. Here they are assigned exactly as we needed. So this is how you can implement k-means clustering algorithm using Python code. If you had any problems or issues, have any comments or questions, let me know and I'll get back to you. Hierarchical clustering. Hierarchical clustering is an unsupervised learning algorithm that builds a hierarchy of clusters. It starts with each data point as its own cluster and then merges or splits clusters based on distance measures, forming a tree-like structure called a dendrogram. The hierarchy can be used to choose a suitable number of clusters by cutting the tree at a specific level. Let's go ahead and implement the hierarchical clustering algorithm and visualizing it with a dendrogram in Python. So I'm going to open an empty blank file and start with importing the necessary libraries. First, I need dendrogram and linkage from scipy.cluster.hierarchy. This imports the dendrogram and linkage functions from scipy.cluster.hierarchy module. Now the linkage performs hierarchical or agglomerative clustering, whereas dendrogram generates a dendrogram plot to visualize the hierarchical clustering. Next, import matplotlib pyplot as plot, which imports the matplotlib.pyplot, which provides functions for plotting graphs and visualizations. It is commonly used for visualizing data in Python. Next, we are going to import numpy as np, which imports the numpy library, which is essential for handling arrays and performing numerical operations in Python. Next, let's get some sample data similar to the last example that we had, where we are taking points in 2D space, np.array, which is equal to x. Now that defines the feature data x as a numpy array, where each sublist represents a data point in 2D space with two values, x and y coordinates. For example, 1, 2 and 10, 2 are 2 points in 2D space. The shape of x is 6, 2, indicating 6 data points with 2 features each. Now let's go perform hierarchical or agglomerative clustering. This can be done by z equal to linkage, pass it x, and method equal to ward. Now ward minimizes variance with clusters. What it does is this function performs hierarchical clustering on x and returns the hierarchical clustering result in the variable z. Now x here is the data points to be clustered, and method equal to ward specifies the linkage criterion. Here, ward is used, which minimizes the variance within clusters at each step, resulting in a compact and spherical clusters. Other linkage methods include single, complete, and average, which calculates distance between clusters in different ways. And finally, Z stores the results of the clustering process as an array, where each row represents a merge containing information on the clusters that were merged, the distance between them, and the number of original data points in the newly formed cluster. So let's go ahead and plot our dendrogram. First, plt.figure fixed size 8,4. This creates a new figure for the plot with a specific size of 8 by 4 inches, which makes the dendrogram more readable. Next, I'm saying dendrogram Z. This plots the dendrogram using the hierarchical clustering results Z. The dendrogram visually represents the merging process of clusters where each U-shaped link shows the distance at which clusters were merged. The x-axis displays the individual data points and the y-axis shows the distance between merged clusters. Now I'm going to give a title to this. I'm going to say dendrogram for hierarchical clustering. Next, I'm going to give an x label, which is data points. This sets the label for the x-axis. And next, y label, I'll say distance, sets the label for y-axis. And finally, I'll say plot.show. This displays the dendrogram plot visualizing the hierarchical clustering process. The height of each merged y-axis indicates the distance between clusters, and cutting the dendrogram at different levels can yield different number of clusters. Let's look at it in real time of how it looks like. I'm going to go ahead and say Python hierarchical clustering, run it, and here you go. Here is our dendrogram. If you see, it has all these U-shaped based on the merging and clusters that it created. So this is how a dendrogram looks like if you have never seen one before. Now this code here performs hierarchical clustering on a set of 2D points and visualizes the results with the dendrogram, as you saw, which shows how clusters are formed by merging data points and group step by step. The dendrogram allows you to identify a suitable number of clusters by selecting a threshold distance. So I hope you were able to implement it. If you had any issues or problems or have any questions, let me know and I'll get back to you. dbScan, or also called as density-based spatial clustering of applications with noise, and that's the reason we call it dbScan. dbScan is an unsupervised clustering algorithm that groups data points based on density, making it particularly effective for identifying clusters of arbitrary shapes and for handling noise, which is outliers. Now, dbScan requires two parameters. One is the EPS, which is the maximum distance between 2 points to be considered neighbors, and minimum samples, which is the minimum number of points required to form a dense region. So let's go ahead and implement and code for dbScan in Python. So go ahead. I have a profile already open. I'm going to first start with importing the necessary libraries. From sklearn.cluster, import dbScan. This imports the dbScan class from scikit's learn cluster module. dbScan is a density-based clustering algorithm that groups data points that are close to each other based on distance and density, and labels points that don't belong to any cluster as noise. Next, we'll import numpy as np, which imports the numpy library, which provides support for numerical operation and array manipulation in Python. Next, I'm going to get some sample data. I'm going to use the same one as previous example, which are points in 2D space. So I have those points available here. Here, x equal to np array defines the feature data x as a numpy array where each sublist represents data points in 2D space with two values, x and y coordinates. For example, the coordinate 1, 2 and also 8, 7 are 2 points in 2D space. The shape of X is 6, 2, meaning there are 6 data points with 2 features each. Next, let's initialize and fit the model. So to initialize, I'll say dbscan EPS equal to 3, min samples equal to 2. As I mentioned earlier, this initializes a dbscan clustering model with the following parameters. EPS equal to 3 specifies the maximum distance between the two samples for them to be considered as in the same neighborhood. The distance defines the reachability of points. Min samples equal to 2 specifies the minimum number of points required in a neighborhood for a point to be considered a core point. If a point has at least min samples points within its EPS radius, it forms a cluster. Otherwise, it may be labeled as noise if it doesn't belong to any cluster. Next, let's do dbscan dot fit x. This fits the dbscan model to data x. dbscan forms clusters based on the density of points, where each point is classified as either a core point, a border point, or noise. The algorithm does not require specifying the number of clusters in advance, as it finds clusters based on the density. So let's go and get the labels. -1 indicates noise in this case. So I'm going to start with labels equal to dbscan dot labels underscore. Now the labels, this retrieves the labels assigned to each data point in X after fitting the model. Each label represents the cluster to which the point belongs. Points that are part of a cluster are assigned to a positive integer label. Points that are considered noise, that is, they don't belong to the cluster, are assigned to label of -1. Let's go ahead and print these labels to see how it looks like. So I'm going to save this and go to my command prompt or terminal and say python dbscan, run this, and you'll see labels 0, 0, 0, 1, 1, -1 based on these points that we have. These are the labels that are created for these, which means this last point, which is pretty much outside of the numbers that we have here, are considered as noise, and others are considered as one cluster. These ones are considered as cluster 1, so that's how they are labeled here. So this code demonstrates how to use dbscan to cluster points in 2D space. dbscan is useful for identifying clusters or arbitrary shape and handling noise, which is represented by points with the labels -1. The algorithm groups points that have a high density and identifies sparse isolated points as noise. So I hope you were able to follow along. If you have any questions or had any issues, let me know and I'll get back to you. Gaussian mixture models, or GMM. Gaussian mixture models is a probabilistic clustering algorithm that assumes data points are generated from a mixture of several Gaussian distributions with unknown parameters. Now, GMM assigns a probability to each data point for belonging to each cluster, making it a soft clustering technique. It is particularly useful when clusters have different shapes or densities. Let's go ahead and implement this Gaussian mixture model GMM clustering in Python. So I have already created a file. I'm going to go ahead and first import the necessary libraries. Next, I'm going to from sklearn mixture import Gaussian mixture, which import the Gaussian mixture class from scikit-learn's mixture module. Now, Gaussian mixture is a clustering model that assumes that data is generated from mixture of multiple Gaussian distributions. It is used for identifying clusters in data when clusters may have elliptical shapes. So next, let's import numpy as np, which imports numpy library which provides support for numerical operations and array manipulation in array. Next, let's get our sample data that we've used before, which are points in 2D space, x equal to np array, and I've given all these points, which defines the feature data x as a numpy array, where each sublist represents a data point in 2D space with two values, x and y coordinates. For example, 1, 2 and 8, 7 are 2 points in 2D space. The shape of x is 6, 2, meaning there are 6 data points with 2 features each. Next, let's go ahead and initialize and fit the model. So I'm initializing the model by saying Gaussian mixture n components equal to 2, random state equal to 42. This initializes a Gaussian mixture model with the following parameters of n components equal to 2, which specifies the number of Gaussian distributions or clusters to fit to the data. This parameter represents the assumed number of clusters in the data. Random state equal to 42. It sets a random seed for reproducibility, ensuring the initialization of the model is the same each time the code is run. Let's go ahead and fit it. gmm.fit pass x. This fits the Gaussian mixture model to the data x. During this process, the model estimates the parameters of the Gaussian distribution, mean and covariance that best describe each cluster in the data. Let's get the cluster labels and probabilities. Labels equal to gmm.predict and probabilities equal to gmm.predictproba. These are the functions. The first one predicts the cluster labels for each data point in X. The predict method assigns each data point to the cluster with the highest probability. The output is an array of integer labels representing the cluster to which each point belongs. The second line number 14, calculates the probability that each data point belongs to each cluster. The predict proba method outputs an array where each row represents a data point and each column represents a cluster. The values indicate the probability that each point belongs to each cluster, providing a soft clustering assignment that is allowing each point to have a probability distribution over clusters. Now let's go ahead and print the cluster labels and print the cluster probabilities out. So let's go ahead and run this on our command prompt or terminal. I'm going to say Python Gaussian mixture models, run it. And here you go. Based on the numbers that we have provided, it's going to create cluster labels for each one of them. This one is very separate, so that's why, since we said 2, it created 2 different clusters, 0 and 1. And here are the cluster probabilities, which is very high, 1 and 0, so that means it's good probability that they are in 2 different clusters. Now this code here demonstrates how to use a Gaussian mixture model for clustering points in 2D space. Unlike k-means, which we did earlier, which assigns hard cluster labels, GMM provides soft cluster assignments by assigning each point a probability distribution over clusters, making it particularly useful for overlapping or elliptical clusters. So if you have any questions or any issues while implementing this, let me know and I'll get back to you. Principal Component Analysis, or PCA. Principal component analysis is a dimensionality reduction technique used to transform a high dimensional dataset into a lower dimensional one by identifying the directions, which is the principal components that capture the maximum variance in the data. PCA is widely used for data visualization, noise reduction, and speeding up machine learning algorithms by reducing the number of features. Let's go ahead and implement this using scikit-learn and running through line by line in Python. So I'm going to go ahead. I've already created a file. I'm going to say import necessary libraries. In this particular case, I'm going to first from sklearn.decomposition import PCA, which imports the PCA class from scikit-learn's decomposition module. Now, PCA is dimensionality reduction technique that transforms data into a lower dimensional space by identifying the directions which are principal components that capture the most variance in the data. Next, import numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulation in Python. Next, let's go and get some sample data. This time I'm getting points in a 3D space. X equal to np array, which defines the feature data x as a numpy array where each sublist represents a data point in 3D space with 3 values x, y, and z coordinates. For example, 1, 2, 3, and 5, 6, 7 are 2 points in 3D space. The shape of x is 5, 3, meaning there are 5 data points with 3 features each. Next, go ahead and initialize and fit the model. So first PCA equal to PCA and components equal to 2. This initializes a PCA model with the following parameters of n components equal to 2, which specifies the number of principal components which are dimensions to keep. Here, n components equal to means we are reducing the data from a 3D to a 2D object. Next, we will gonna say x reduced equal PCA.fit transform x. This fits the PCA model to the data x and transform it into a lower dimensional space. The fit transform both fits the model, finding the principal components, and transforms the data based on these components, resulting in x reduced, which has a shape of 5, 2. Now let's go ahead and print the reduced data and print the explained variance ratio for this. Now here, x underscore reduced prints the transformed data in the reduced 2D space. Now each row in x reduced represents a data point in 2D space where each value represents the projection of the original data onto the first and the second principal components. This one, the second one, prints the explained variance ratio, which indicates how much of the total variance in the original data is captured by each principal component. The function PCA dot explained variance ratio underscore is an array where each value represents the proportion of variance explained by a principal component. This information is helpful for understanding how much information is retained in the reduced dimensional representation. So let's go ahead and run it in our command prompt. I'm going to clear the previous one, and I'm going to say here, make sure it's saved. Say Python principal, and you'll see the reduced data is these are the coordinates based on the reduced data, and the explained variance ratio is 0.99, 0.00. So this code demonstrates how to use PCA to reduce the 3D data set to a 2D while retaining as much variance as possible. The explained variance ratio shows the contribution of each principal component to the total variance, providing insight into the effectiveness of the dimensionality reduction. If you had any questions or issues implementing this, let me know and I'll get back to you. T-distributed stochastic neighbor embedding, or TSNE. TSNE is a dimensionality reduction technique primarily used for visualizing high dimensional data in 2D or 3D space. Unlike PCA, TSNE is nonlinear and focuses on preserving the local structure of data, making it highly effective for visualizing clusters. However, it is computationally intensive and best suited for small to medium sized data sets. Let's go ahead and implement this in Python. So I have a file already prepared. I'm going to go ahead and start. First, import necessary libraries. So from sklearn.manifold import tsne. This imports the tsne class from scikit-learn's manifold module. And as I mentioned, tsne is a non-linear dimensionality reduction technique particularly used for visualizing high-dimensional data in 2D or 3D by preserving the local structure of the data points. You need to remember that. Next, import numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulations in Python. Next, let's get the sample data. These are points in high dimensional space. So I have x equal to np array, and I have the points here. Now this defines the feature data x as a numpy array where each sublist represents a data point in a 3D space with 3 values, x, y, and z coordinates. For example, 1, 2, 3, and 5, 6, 8, 5, 7, 8 are 2 points in 3D space. The shape of x is 7, 3, meaning there are 7 data points with 3 features each. Next, let's go ahead and initialize and fit the model. So I have tsne n components equal to 2, random state equal to 42. Here we initialize a tsne model with parameters n components equal to 2, which specifies the target number of dimensions for the reduced data, setting Any components equal to 2 reduces the data from its original 3D form to 2D, making it easier to visualize. Random state equal to 42 sets a random seed for reproducibility, ensuring that each time the code is run, the same TSNE embedding is produced. Next, we'll do x reduced equal to TSNE dot fit transform. This fits the TSNE model to the data x and transforms it into a 2D space. Now, the fit transform both fits the model and applies the transformation, generating x underscore reduced, a new array containing the 2D coordinates for each data point. Unlike PCA, TSNE does not capture variance but instead focuses on preserving local structure. So points that were close in high dimensional space will remain close in the reduced 2D space. Now finally, let's go ahead and print the reduced data in x underscore reduced, which prints the transformed data in the reduced 2D space. Now each row in x reduced represents a data point in the 2D space where the values correspond to the new coordinates derived through the TSNE transformation. Let's go ahead and run this. Python t-sne.py, run it, look at my points. Now when I run this particular code, I see a value error perplexity must be less than n samples, and I've not mentioned that. So I'm going to clear this out. I'm going to go here, and one of the things that I forgot was TSNE and components 2. I have to give here perplexity equal to 5. That's another parameter that I missed. Now this one, perplexity, is a parameter in TSNE that controls the balance between local and global aspects of the data in the embedding. It's usually recommended to set it between 5 and 50. Setting perplexity to 5 should work with 7 data points. However, if your data set grows, you may increase the perplexity to optimize the TSNE output. So let's go ahead and run it again. And there you go. Let's compare. So if you see these points, this is kind of reduced to 2D, but making sure that they are in the same dimension. So now what we did here was this code kind of demonstrate how to use TSNE to reduce a data set from 3D to 2D for visualization purposes. Now TSNE is kind of particularly effective at creating visually interpretable representations of complex high dimensional data by clustering similar points close together, revealing patterns that may not be apparent in higher dimensions. So I hope this helps, and if you had any issues or have any more questions on this, let me know and I'll get back to you. Autoencoders. Autoencoders are neural networks used for unsupervised learning, specifically for dimensionality reduction and feature extraction. They work by encoding input data into a compressed latent representation and then reconstructing the original input from this representation. Autoencoders are useful for tasks like denoising, anomaly detection, and pre-training for other neural networks. So let's go ahead and implement a detailed line-by-line code for implementing an autoencoder in Python we'll use TensorFlow and Keras in this particular example. So first step is to import tensorflow.keras.model, import model from there. So I'm going to go ahead and import necessary libraries, which is this one. What this does is imports the model class from TensorFlow Keras models, allowing you to create and combine the input and output layers to define the entire autoencoder model. Next, from tensorflow.keras.layers, import input and dense. This imports the input and dense classes from TensorFlow Keras layers. Input is used to specify the input layers of the model where you define the shape of the input data. And dense is a fully connected neural network layer commonly used in feed-forward networks. Here it's used in both the encoder and decoder parts of the autoencoder. Next, import NumPy as NP. This imports the NumPy library for array manipulation and numerical operations in Python. Let's go ahead and get the sample data, which is points in 5-dimensional space. So I'm going to say x equal to np array. Now this is this public array defines the feature data x as numpy array with data points in 5-dimensional space. Now each sublist represents a data point with 5 values which are features. Now for example, that first point 1, 2, 3, 4, 5 is a 1 point in 5D space. The shape of x is 6, 5, meaning there are 6 data points with 5 features each. Now let's go ahead and define the autoencoder model. You can just say input dim equal to x dot shape of 1. This sets the variable input dim to the number of features in the data set x. Now when I say dim is dimensions, in this case it's 5. X dot shape of 1 returns the number of columns which are features in x, which will be the input dimension for the autoencoder. Next, I'm going to say encoding dimension equal to 2. So this specifies the encoding dimension, that is the number of dimensions to which we want to compress the input data. Here we set it to 2 to compress the 5-dimensional input into a 2-dimensional representation. Next, let's go ahead and do the encoder. Input layer equal to input shape equal to input dim, comma. This defines the input layer of the autoencoder with the shape of input dimension, where input dim is 5. This specifies that each input data points has 5 features. Next, encoded equal to dense, encoding dim, and activation equal to relu, input layer. This defines the encoder layer, which is dense, fully connected layer, with encoding dim neurons, 2 neurons in this case. The activation function used is relu, which is rectified linear unit, which introduces non-linearity to the model. The encoder reduces the input dimension from 5 to 2 by learning a compressed representation of the input data in this case. Next, I'm going to do the decoder. So decoded equal to dense input dim and activations equal to sigmoid encoded. So this defines the decoder layer, which is also a dense layer with input dim neurons, or 5 neurons in this case, to reconstruct the original input. The sigmoid activation function outputs values between 0 and 1, commonly used for reconstruction tasks. The decoder expands the compressed 2-dimensional encoding back to the original 5-dimensional space. Next, let's do the autoencoder model. I will say autoencoder equal to model input layers, comma, decoded. Now this combines the input and the output layers to create the full autoencoder model. This model takes input layer as the input and decoded as the output, meaning it will take a 5D input, compress it to 2D in the encoder, and then reconstruct it back to a 5D in the decoder. Now finally, let's compile the model. Let's say autoencoder dot compile optimizer equal to Adam, loss equal to MSE. Now this compiles the autoencoder model specifying optimizer equal to Adam, which uses the Adam optimizer, an adaptive learning rate optimization algorithm commonly used for training deep learning models. And loss equal to MSE specifies mean square error MSE as the loss function, which calculates the average of squared differences between reconstructed and original input values. Lower loss indicates better reconstruction accuracy. Next, let's train the model. Once your autoencoder dot fit x comma x epochs equal to 100, batch size 2, and verbose 0. This trains the autoencoder model on the dataset x, where x is used as both the input and target. The model tries to reconstruct its own input in this case. Epochs equal to 100 specifies that the model will iterate over the entire dataset 100 times. Batch size equal to 2, the model processes 2 samples at a time before updating its weights, which helps stabilize training. And verbose equal to 0 suppresses the output of the training progress for cleaner output. Next, let's get the encoded compressed representation by saying encoder equal to model input layer encoded. This defines an encoder model using only the encoding part of the original autoencoder. This model takes input layer as input and outputs encoded, allowing it to generate compressed representations. X compressed equal to encoder.predict. This what it does is it passes the input data x through the encoder model to obtain the compressed two-dimensional representation. The X compressed now contains the 2D representation of the original 5D input data. Next, let's go ahead and print the compressed representation. So this will print the compressed two-dimensional representation of the input data, allowing us to view the lower dimensional encoding learned by the autoencoder. Let's see how it looks like. Go here and say Python autoencoder py. It's going to run through the model, and here you go. We have the data here, the compressed representation. It shows the data here based on the data that we have sent here. So this this code kind of trains an autoencoder to reduce 5-dimensionality data to two-dimensional two dimensions here, which can then be used for tasks like visualization or feature extraction. The autoencoder learns to reconstruct the original data while compressing it into more compact two-dimensional form in the middle layer. The encoder part of the model can be used separately to generate compressed representation of the new data. So if you have any problems or had any issues implementing this, or have any questions for me, let me know and I'll get back to you. Self-training. Self-training is a semi-supervised learning approach that leverages a small labeled dataset alongside a larger unlabeled dataset. The model is initially trained on labeled data, and then it makes predictions on the unlabeled data. The confident predictions, those with high certainty, are then added to the labeled dataset, and the process is repeated to improve the model. Let's go ahead and build this code in Python to see how this can be done. So let me open my IDE, and here I've already created a file called as selftraining.py. Now here, first step is to import the necessary libraries. So I'm going to go ahead and start with my libraries. First, from sklearn ensemble import random forest classifier. This imports the random forest classifier class from scikit-learn's ensemble module, which is used for supervised classification tasks. Next, from sklearn.datasets, import make classification. This imports the make classification function, which generates a synthetic dataset for classification tasks. Next, from sklearn.model selection, import train test split. This imports the train test split function, which splits a dataset into training and testing subsets. Next, from sklearn.metrics, import accuracy score. This imports accuracy score, which calculates the accuracy of predictions. Finally, let's import numpy as np, which imports the numpy library for numerical operations like array manipulation. Let's go ahead and generate a synthetic data set. So I'm going to say x, y, make classification, n samples equal to 200, n features equal to 5, random state equal to 42. This generates a synthetic data set with 200 samples and 5 features using random state equal to 42 for reproducibility. Next, let's say x labeled, x unlabeled, y labeled equal to train test split x, y, test size 0.7, random state equal to 42. What this does is this splits the dataset into labeled and unlabeled portions, with 30% labeled for initial training and 70% unlabeled. X underscore labeled and y underscore labeled hold the labeled data, while x underscore unlabeled contains the unlabeled data. Its labels are ignored for the self-training approach here. So let's go ahead and initialize and train the model with labeled data. So I say model equal to random forest classifier, random state equal to 42, which will initialize a random forest classifier with random state equal to 42 to ensure reproducibility. And then I'm going to say model.fit x labeled, y labeled. This trains the model on the initially labeled data. Now let's go and perform self-training on unlabeled data. For this, I'm going to say for underscore in range 5, which sets a loop to repeat the self-training process 5 times, allowing the model to iteratively expand its labeled dataset by adding confident predictions. Next, go ahead and predict the probabilities of unlabeled data. So I'm going to say props equal to model.predictproba x underscore unlabeled. This uses the model to predict class probabilities for each sample in the unlabeled data set. Next, I'm going to say high confidence IDX or index equal to np.where np.max props x is equal to 1 greater than 0.9 of 0. What this does is this finds indices of samples where the model's maximum probability exceeds 0.9, including high confidence in these predictions. So that's what this does. Next, I'm going to say add high confidence predictions to label data. To do that, I'm going to say x labeled equal to np.vstack and pass it x labeled comma x unlabeled high confidence IDX. This adds the high confidence samples from x underscore unlabeled to the x labeled data set using np.vstack. Next, I'm going to say y labeled equal to np hstack. And what this does is this adds the corresponding predicted labels for these high confidence samples to y labeled using np.hstack. Next, I'm going to remove confident samples from the unlabeled data set. To do that, I'm going to say x underscore unlabeled equal to np.delete x unlabeled high confidence IDX and axis equal to 0. So this will remove the confident samples from x unlabeled, leaving only uncertain samples for the next iteration. Then I'm going to say retrain the model on expanded labeled data set. So I'm going to say model.fit x labeled and y labeled, which retrains the model on the expanded labeled data set, incorporating new samples from each iteration. Now final evaluation of a test set. To do that, what I'm going to do is I'm going to say x underscore train x test, y train y test, train test split, and to this pass x comma y test size equal to 0.3, random state 42. This splits the original data into a training and test set, 70% for training, 30% for test. Then I'm going to say model.fit, which trains the model on the full training set. Then I'm going to say ypred equal to model.predict x underscore test. This predicts labels for the test set. Then accuracy equal to accuracy score, which computes the accuracy on predictions on the test set. And finally, I will print the accuracy. This prints the final accuracy score, providing a performance measure for the self-trained model. Let's go ahead and run this particular project. So I'm going to save it and open my terminal. Inside my terminal, I'll say python self-training.py. And there you go. It shows me an accuracy of 0.8833, which is pretty good. And hopefully you were able to follow along and implement this. If you had any issues or problems, let me know and I'll get back to you. Q-learning. Q-learning is a model-free reinforcement learning algorithm used to find the optimal action selection policy for a given problem. It learns by interacting with an environment, updating a Q table, a matrix of state action values, and maximizing the expected cumulative reward. Q-learning is effective in problems where the environment can be represented by discrete states and actions. So let's get started with the line-by-line implementation of Q-learning code. I'm going to start with an empty file, qlearning.py. Here, first let's import our libraries. I need import numpy as np, which imports the numpy library used for numerical operations, including creating and manipulating the Q table. Then we are going to import random. This imports Python's random module used for random choices within the code. Next, let's define the environment, which is a 4x4 grid. So we start with number of states equal to 16, which is 4x4 grid. Number of actions equal to 4 up, right, left, and down and left. Q underscore table equal to np.zeros, number of states and number of actions. Here, the first one, number of states equal to 16, it defines the total number of states in a 4x4 grid. So you can think of it as like 16 cells in total. The next line, number of actions equal to 4, defines the total number of possible actions. 0 equal to up, 1 equal to right, 2 equal to down, and 3 equal to left. Those are the 4 actions, 0 to 3. Next, we have Q table equal to np zeros. What this does is this initializes a Q table with 0 values It has 16 rows, 1 per state, and 4 columns, 1 per action, which will be updated with learned Q values representing expected rewards for each state action pair. So let's get started. Next step is defining the parameters. Alpha equal to 0.1. This is the learning rate or sets the learning rate which determines the extent to which new information overrides the old information. Gamma equal to 0.9. This sets the discount factor which controls how much weight future rewards hold compared to immediate rewards. We have epsilon equal to 0.2. This sets the exploration rate which determines the likelihood of choosing a random action instead of the best known action. Next is number of episodes equal to 1000. This defines the number of episodes, which are iterations the agent will go through to learn. So next, let's define a simple reward structure. So I'm going to say rewards equal to np zeros number of states. This initializes an array to store rewards for each state, initially setting all rewards to 0. Rewards of 15 equal to 1. This sets a reward of 1 for the goal state, which is state equal to 15, while all other states remain at reward of 0. So let's go ahead and let's create a function to determine the next state based on the action. So create define next state function, get next state function with state and action inside here. Now if action equal to 0 and state is greater than equal to 4, it is an up action. So I'm going to say return state equal to -4. Else, if action equal to 1 and the state plus 1 mod 4 is not equal to 0, that means you have to move right. So I'll return state plus 1. If the action is equal to 2 and state is less than 12, then it's down movement. So I'm going to say return state plus 4. Next, I'm going to say action equal to 3 and the state mod 4 is not equal to 0. That means it's a left motion. So I'm going to say return state equal to -1. And finally, I'll say else return state. In this case, if this returns the same state if the action would go out of bounds. So that's why this one is very important. Again, so this particular function define next get next state defines a function that calculates the next state based on the current state and the action while ensuring the agent doesn't move out of the grid boundaries. The first action equal to 0, which is up, moves up if the agent is not in the top row. Action 1 right moves right if the agent is not on the right edge. Action 2 down moves down if the agent is not in the bottom row. Action 3, which is left, moves left if the agent is not on the left edge. And finally else, as I mentioned, returns the same state if the action would go out of bounds. So let's go ahead and implement the Q learning algorithm now. Now here, I'm going to say for episode in range of number of episodes, this loops through each episode, allowing the agent to learn iteratively. I'm going to say state equal to random dot rand int 0 comma number of state -1. This selects a random starting state for each episode. Now while state is not equal to 15, now this continues each episode until the agent reaches the goal state, which is state of 15. So for this, I'm going to say if random dot uniform 0 comma 1 is less than epsilon, then so in this particular case, what happens is chooses an action based on the epsilon greedy policy, which allows exploration and exploitation, where you can say action equal to random dot rand int 0 comma number of actions is -1. What this does is selects a random action for exploration. Else it will say np dot argmax q table state, or selects the best action by choosing the one with the highest q value in the current state for exploration. Next, let's go get the next state. Next state equal to get next state, state of action. This calls get next state to get the new state based on the current state and chosen action. Next, I'm going to say reward next state. This retrieves the reward for moving to the next stage. Next, old value equal to q table state comma action. This stores the current q value of the state action pair for future updates. And next, we're going to say next max equal to np dot max Q table next state. This gets the highest Q value of the next state to calculate expected future rewards. Now let's go ahead and do the Q learning update rule. So it's a new value equal to old value plus alpha times reward plus gamma times next max minus old value. This updates the Q value for the current state action pair using the Q learning formula, which balances immediate and future rewards. Next, I'm going to say Q table state and action equal to new value. This stores the updated Q value in the Q table. Then we'll say state equal to next state. This will move to the next state for the next iteration, continuing until the goal state is reached. So I'm going to go ahead and finally display the learned Q table right now. So I'm going to say print learned Q table and pass the Q table here. This displays the final Q table after training, showing learned Q values for each state action pair. These values represent the expected reward for each action in each state learned over the episode. So let's go ahead and first I'll save it, open my terminal and say Python Q learning.py. And there you go, that's our Q table, which defines our 16 by 16 4 by 4 state with all the different parameters in my table displayed right here. If you were able to do this, that's great. If you had any questions or issues while implementing this, let me know and I'll get back to you. So I hope you were able to understand the Q learning algorithm. If you have any questions, again, leave them in the comments. Deep Q networks or DQN. DQN is a reinforcement learning algorithm that combines Q learning with deep neural networks. It uses a neural network to approximate the Q values for each action in a given state, allowing it to handle environments with high dimensional and continuous state spaces. DQN uses experience replay, storing past experiences and training on random batches, and a target network to stabilize training. Let's look at line by line implementation for DQN. So I'm going to go ahead, start with an empty file, deepq networks. First, let's import our libraries. So I need import gym. Now gym provides the environment interface for reinforcement learning. Example, in our case, we're going to use Cardpole version 1. Next, we'll need torch. We need torch NN, and we'll need torch optim as optim. So PyTorch libraries, these are the PyTorch libraries that is used to build and train the DeepQ network, which is DQN in our case. Next, import NumPy is used for numerical operations, especially for arrays and converting data formats. Then we're going to import random. Now this is Python's random library used here for sampling random actions and selecting batches from the replay buffer. Next, let's go ahead and define the DQN model. So for DQN model, I'm going to say class DQN and pass NN module as a parameter. This DQN class inherits from NN.module, making it a PyTorch neural network model. So first thing that I need is initialize the DQN model with 3 fully connected linear layers. So that is, I'm saying the function in it with self, input size and output size. So for this, I'll add self. First, I'll call the super method. Then I'm going to say self.linear1 equal to nn.linear input size of 64. This is the first layer that takes input size, which is number of state features, as the input and output 64 features. Next, I'm going to say self.linear equal to nn.linear 64 by 32. This is the second layer, processes the 64 features and outputs 32 features. And then I have self.linear 3. This is the final layer that outputs output size values, 1 for each possible action. So that's how you initialize the DQN model with 3 fully connected layers. Next, let's create the forward method that defines the forward pass of the model. It applies ReLU activation to self.linear1 and self.linear2 layers, and no activation on the third layer or the final layer is needed as it outputs Q values directly. Next, let's define the hyperparameters. So for this, I'll have the different hyperparameters including environment name, which is Cardpole v1, which specifies the gym environment. Next, I have the learning rate of 0.001 is the learning rate for the Adam optimizer. I need a gamma, which is the discount factor for future rewards. I'll use a buffer size, which is the maximum number of experiences to store in the replay buffer. I'll need a batch size of 32, which is the number of experiences sampled from the replay buffer per training step. Need epsilon 0.1, which is the exploration rate for epsilon greedy action selection. And then I'll need the target update frequency, which is number of steps between target network updates. So next thing that I'm going to do is I'm going to initialize environment and DQN model. So I'm going to say here env equal to gem dot make env name. Now env creates the gem environment specified by the environment name. Next I'm going to say input size equal to environment dot observation space dot shape 0. What it does is it sets the input size for the DQN model based on the state dimension here, and then output size equal to environment dot action dot space dot n underscore space dot n, which sets the output size for the DQN model based on the number of possible actions. Next, I need the device equal to torch device CUDA if torch.CUDA is available, else CPU. This sets the competition device, either GPU if it's available, other CPU. And since I'm learning on my local laptop, it's going to just use the CPU. Next, policy net equal to DQN, input size, output size to device. This is the main DQN model for action selection. Next is my target net. This is a secondary DQN model used to compute target Q values and updated periodical for stability. Next, I have target.net load state dictionary. So what this does is initializes target net with policy nets widgets. That's why it says the parameter that is passed is policy net dot state dictionary. Next, I'm going to say target underscore net dot eval. This puts target net in evaluation mode, disabling gradient update for stability. Now let's go ahead and create the optimizer. Optim add dot adam policy net dot parameters and LR equal to learning rate. So I'm passing those. So this creates the Adam optimizer for updating policy nets widgets weights. So next is criterion nn.mse loss. So this is mean squared error loss for training, which measures the difference between the predicted and the target Q values. Next, let's go ahead and add the replay buffer. So I'm going to create a replay buffer equal to empty. This stores past experiences for experience replay. Experiences are tuples of, it contains state, action, reward, next state, and done. So let's go ahead and run the training function. So this is our training function that trains the agent over a specified number of episodes. I'm going to set the step count equal to 0, which keeps track of the total steps for the target network updates. We're going to use probably like around 1,000. And then let's go ahead and run the episode loop. So what I'm going to do here is I'm going to say for episode in range, depending on number of episodes that are passed to me. So this loops through each episode for training, and it will set the state underscore equal to environment reset. This resets the environment at the start of each episode. Next, I'm going to say state equal to np.array state. This ensures state is the numpy array for later conversion to PyTorch tensors. And then I'll have my done equal to false, where what this does is this initializes the done flag to keep track of episode end. I'll have total reward equal to 0. It accumulates reward per episode. Next, I'm going to say while not done, this is the inner loop where the agent interacts with the environment until the episode ends. So let's go through the episode. So this is the epsilon greedy action selection. So for that, I'm going to say if random.random is less than epsilon, action should be environment.action underscore space dot sample. Else, in the other case, like so, first with probability epsilon, choose a random action. Otherwise, use policy net to choose the action with the highest predicted Q value. So that's what this does here. So you have specified action equal to policy net torch.tensor, pass the state, give the d type equal to torch.float, device equal to device, and argmax item. So this will take care of that. Next, let's take action and observe reward and next state. So in this particular case, so I'm going to say next state, comma reward done truncated underscore equal to environment step action. This takes the selected action receiving the next state, reward, and flags for completion. Then I'll do done equal to done or truncated. This sets done to true if either done or truncated is true, ending the episode if the agent reaches the goal or the time limit. Next, I'm going to say next state equal to np dot array next state and pass the total reward equal to plus equal to reward. This updates the cumulative reward for this particular episode. So that's what it happens here. Now next, I'm going to go store the experience in the replay buffer. So for this first thing, I'm going to set the replay buffer dot append state action reward next state and done. What it does is it adds the experience to the replay buffer. Next, I'm going to say if length of replay buffer is greater than buffer size, then remove the oldest experience. So that I can do by saying replay buffer pop 0. Next, I'm going to say state. So now I'm going to update the state equal to next state. This update stage to the next state for the next step. So let's go ahead and for experience replay and training, let's sample a batch from the replay buffer. So I'm going to say if length of replay buffer is greater than equal to batch buffer, batch size, what this does is it ensures enough samples in the replay buffer before training. Then I want to do is batch equal to random.sample. This samples a mini batch from the buffer. Next, I'll say states, actions, rewards, next states, done's equal to zip star batch. What this does is this unpacks the batch into separate components. So once that is done, I'm going to convert these batches to tensors. To do that, I'm going to say state equal to torch dot tensor states d type torch dot float and device equal to device. So this will convert each batch component to a PyTorch tensor of the correct device. So for this is for states, then I'll do for the action similar stuff, I'll do for rewards, I'll do for next steps, and then for done's I'll do this. So I have all these different ones converted the batch to tensors. So that's why you use torch tensor. Next, I am going to compute the Q value and the target Q values. To do that, I'm going to say current Q values equal to policy net states dot gather 1 comma action unsqueeze. This computes Q values for actions taken using policy net. And then next Q values, target net. So this computes the Q values of the next state using target underscore net. And then target underscore Q values is rewards plus gamma times next Q values times 1 minus done's. So this calculates the target Q values based on rewards and future Q values accumulating, accounting for episode termination. So that kind of brings us almost close to the end, where next I need to probably go ahead and optimize the model. So I'm going to compute loss and update the policy network by saying loss equal to criterion current Q values target Q values dot unsqueeze. This calculates MSE between current and the Q and the target Q values. Then I'm going to say optimizer dot zero grad. This clears previous gradients, and then loss dot backward. This computes the gradients and finally update the model parameters using optimizer dot step. Now let's go ahead and finally update the target network by saying update target network step count plus equal to 1, and if step count mod target update frequency equal to 0, target dot net target underscore net dot load state dictionary policy underscore net dot state dictionary. What this does is this updates the target net periodically with policy net weights for stability. So that's what happened here. Now finally go ahead and print the episode and the total reward that is got, and now that we are ready, we can just go ahead and run the training. So I'm going to say train number of episodes equal to 1000. You can reduce it just to check for a quicker, but I'm going to run it for a little while so it reaches its destination very easily. So I have all the code ready now here for our DQN or DeepQ networks algorithm. next step is to run this. So let's go ahead and say Python deep Q network, and it's going to start running, going through each episode and then calculating the total reward. I'm going to give it some time because I said 1000 and I'm at like 160 right now. I'll come back in some time and continue with this. So it took some time and it completed our entire code, and it has trained our network, and we have a model available to use. So that's your deep Q network algorithm, and that's how you can use it. If you had any issues or problems implementing this, let me know in the comments and I'll get back to you. Policy gradient methods. Policy gradient methods are a class of reinforcement learning algorithms that learn a policy directly by optimizing the parameters of a policy network. Instead of learning Q values like Q learning or DQN, policy gradient methods focus on finding the optimal action selection strategy that maximizes cumulative rewards. A popular approach is the reinforce algorithm, where actions are sampled for a policy distribution and the policy is updated using gradients based on rewards. Let's go ahead and look at line by line implementation of policy gradients methods. So I'm going to start with an empty file. I called it policygradient-methods.py. Let's go ahead and import our NumPy, which provides support for arrays and numerical computations. Then we'll get TensorFlow STF. This is used for defining and training the neural network, which is also from TensorFlow Keras import layers that will be used for that. And I'm going to import Gem, which provides the environment interface here for the cart pole v1 environment. So let's go ahead and set up the environment. First, I'm going to say environment is gem.make cart pole v1, state shape equal to environment observation shape 0, and this kind of gets the number of state features, example position or velocity, and the number of actions equal to env.actionspace.n. This defines the number of possible actions left or right in the cart pole environment. Let's go and define the parameters. Learning rate equal to 0.01. This sets the step size for the optimizer to update the network weights. Gamma, I'm going to set 0.99. This sets the discount factor, determining how much future rewards are considered. Next, building the policy. So for policy network, I'm going to say define build policy model. And here I am going to say model equal to tf.keras.sequential. Now this function defines this is a function that defines how to create the policy network. Now tf.keras.sequential, what it does is it's a sequential model where each layer feeds into the next. So let's go ahead and create these different layers here. So the first one is layers.dense 24 activation ReLU is the first hidden layer with 24 neurons and ReLU activation. So here is the entire one. The second one is the second hidden layer, which also with ReLU, and the third one is the output layer with number of actions output for action probabilities and softmax activation to provide a probability distribution over actions. Now let's go ahead and say model.compile. We pass these parameters. This compiles the model with Adam optimizer. As you can see, tf.keras optimizer Adam is what we're using, and passing learning rate to it. Next, I'm going to return this particular model. So next is to call that build policy model. So I'm going to call that function from the policy model variable, and this will call the model to create an instance of policy model that will be used to predict action probabilities. So next step is to create the action selection function. So here I'm going to create a choose action and pass state as the variable. State equal to np array. What this does is this reshapes state into a 2D array with shape of 1, state shape for model input compatibility. Now I'm going to say probability says policy.model predict state. This uses the policy model to predict the probability distribution over actions. And then finally np.random, this is what I'm going to return, chooses an action based on the predicted probabilities. That's why I'm passing the number of actions and p equal to probabilities at 0. So this function kind of chooses an action based on the policy network's output. Next,
Let's go ahead and do the discounted reward calculation. For that, I'm going to say discount rewards. Here, I'm going to pass the rewards as the input as the parameter. Discount equal to NP zeros like rewards. What this does is it initializes an array to store discounted rewards. None cumulative. I'm going to set the cumulative equal to 0, and then loop through uh, I in reversed range length of rewards, which iterates backward over the rewards, and set the cumulative equal to cumulative times gamma plus rewards of I, which updates the cumulative reward with discounting. Now next I'm going to say discounted I equal to cumulative. This stores the discounted reward and then returns the discounted minus np dot mean discounted, which normalizes the discounted reward by subtracting the mean to stabilize the training. So let's go ahead and work on the training function. So first, train on episode. This function trains the model on data from a single episode. So I say discounted rewards equal to discounted rewards. This calculates the discounted rewards for the episode. Now with tf dot gradient tape as tape, this starts recording operations for automatic differentiation. I'm going to say action prob equal to policy model tf dot converted to tensor states df d type equal to tf dot float 32 training equal to true. What this does is this will calculate action probabilities for each state in states. Next, I'm going to say action indices equal to tf dot stack tf range length of actions axis equal to 1. This prepares indices. This will prepare the indices to select the probability of the action taken. Next step is select action probabilities. This will extract the action probabilities for the chosen actions. So right here, by passing the action props and action indices. And finally, loss equal to minus tf reduce mean tf dot math log selected action props times discounted records. This calculates the policy gradient loss using the negative log probability of selected action weighted by discounted rewards. Next, let's go ahead get the gradients equal to tape dot gradient pass the loss and policy model dot training variables. This computes gradients of the loss with respect to the model's parameters. And next, we're going to say policy underscore model optimizer apply gradient. This updates the model's parameters using the computed gradients right here. So next, let's go ahead and run the main training loop. I'm going to set the number of episodes as last time 2000, and for each episode in this particular episodes, I'm going to say state equal state comma underscore environment reset. This what this does is this resets the environment to start a new episode and handles compatibility with the new gym version where reset returns a tuple. And then episode states, a comma episode actions, episode rewards, everything is set to empty. Initializes this list to store states, actions, and rewards for each episode. So once I have that ready, I'm going to run a while or episode loop where action equal to choose action state. This selects an action using the policy. Next state equal reward done truncated equal to environment dot step action. This takes the action in the environment and gets the resulting state reward and done flags. Then I'm going to get done equal to done or truncated, which again as last time ends the episode if either done or truncated is true. Then I'm going to say episode dot state append state, episode dot action append action, episode rewards append rewards. These stores the state, chosen action, and received rewards in their respective list for each step. Next, I'm going to go through the next step and say state equal to next state, which updates state to the next for the next step in the iteration. I'm going to say if done, what I want to do if it's completed, when episode ends, I'm going to say episode state equal to npv stack, converts the episode states into a 2D numpy array, and then train on episodes. This trains the model on the data from this episode. As you can see, this takes that variables, and finally I'm print the logs here, logs the episode number and the total reward, and then break out of this loop. So this code trains a policy network using policy gradient reinforcement learning on the cardpole v1 environment, and each episode's discounted rewards are used to update the policy network, and actions are selected based on a probability distribution predicted by the network. Let's go ahead and run this. I'm going to save it first and say Python policy, run it. It's going to take some time because it's going to run through 1,000 episodes. So, and currently I am at 7, 8, 9, 10. If you see here, shows the episode number. So I'm going to give it some time and then come back. It's going to take a way lot of time as compared to the last ones because it has to run through the 1,000 episodes. So it took a little bit time, but finally we are at episode 1,000 with a total reward of 500. It took forever to go through this, but if you want to try something, you can just reduce the number of episodes and then train this. If you had any questions or any problems while running this, let me know and I'll get back to you.
One class SVM. One class SVM, where SVM stands for Support Vector Machine, is an algorithm for anomaly detection that identifies data points that differ significantly from the normal distribution of data. It's particularly useful when the data set primarily consists of one class and we want to detect outliers. One class SVM separates the data into a high density region, which is the normal data, and sparse regions, which are the anomalies. Let's go ahead and implement line by line in Python of how to implement one class SVM algorithm. So I have an empty file here, one class svm.py that I've created. First thing I'm going to do is import some libraries. So first, from sklearn.svm, import one class svm. This imports one class svm class from sklearn.svm, which is used for anomaly detection. It is particularly suited for identifying outliers or anomalies in a dataset, as we mentioned. Next, we're going to import numpy as np. This imports numpy, which is used to generate random data and manipulate arrays. Let's go ahead and generate that sample data for training. For first, x equal to 0.3 times np, which is numpy dot random dot randn 100, 2. This creates a set of 100 two-dimensional random points drawn from a normal distribution scaled by 0.3. The points are clustered around 0, 0. Next, I'm going to say x train equal to np.r x plus 2, x minus 2. This creates two clusters for training by shifting points in x. X plus 2 shifts all points by plus 2 in both dimensions, resulting in points clustered around 2, 2. X minus 2, on the other hand, shifts all points by negative 2 in both dimensions, resulting in points clustered around minus 2, minus 2. The np.r underscore x plus 2, x minus 2 concatenates these two clusters vertically to form x underscore train. Now let's go ahead and generate test data with outliers. So I'm going to create this x underscore test np.r underscore x plus 2, x minus 2, and I have another thing here which I'm going to talk about in a second. But this creates test data by combining x plus 2 and x minus 2 clusters, same as the training data, and adding 20 random points as outliers. That is in the second part of the line here, which is np.random.uniform low equal to say minus 6, high equal to plus 6, size equal to 20, 2. This generates the 20 two-dimensional points uniformly distributed between minus 6 and 6, which are likely outside the main clusters. Let's go ahead, initialize and train the model. So first I'm going to say model equal to 1 class svm, gamma equal to auto, and nu equal to 0.1. This initializes the 1 class svm model with gamma, which is auto, sets the kernel coefficient automatically based on the number of features. It controls the influence of each data point with higher values leading to smaller decision regions. And nu equal to 0.1 represents an upper bound on the fraction of training errors, which are anomalies, and a lower bound on the fraction of support vectors. Here it assumes up to 10% of data might be anomalies. Next, I'm going to model.fit xtrain, which trains the model on the xtrain data. Let's go ahead and make the predictions. So this function here, predictions equal to model.predict, will uses the trained model to predict on x test. The one class SVM model assigns -1 to points classified as anomalies and 1 to normal points. So let's go ahead and display these predictions out. I'm going to just print it out. This prints the results where each element in prediction is either 1, which is normal, or -1 anomaly based on the model's classification. So let's go ahead and run this thing. So I'm going to go ahead and say Python 1 class svm.py, and there you go. We have our normal distribution 1 and -1, which are anomalies. So I hope you were able to get through this. If you had any issues, errors, problems, or any questions, let me know in the comments and I'll get back to you. Isolation forest. Isolation forest is an ensemble method for anomaly detection that isolates anomalies rather than profiling normal data. The algorithm randomly selects a feature and a split value to partition the data, creating trees where anomalies are easier to isolate due to their sparse distribution. Anomalies are identified based on their shorter path lengths in the tree structure, as they are isolated faster than the normal points. Let's go and implement this line by line in Python and see how we can build our isolation forest. We'll go ahead, and I've already created a file called as isolationforest.py. Here, I'm going to first step is import the libraries. First, sklearn.ensemble, import isolation forest. This is where you can find it. Import numpy as np. So the first one, isolation forest, it imports the isolation forest class from sklearn ensemble, a widely used algorithm for anomaly detection. Now, isolation forests are efficient for identifying outliers, as I mentioned, by isolating observations through random partitioning. Now, numpy is used here to generate random data and handle arrays, something that we did in the previous algorithm too. So let's go ahead and generate sample data for training. So it's almost same as the last one, x equal to 0, 3 times np.random.randn 100, 2. If you have not heard about this in the previous video, I'm going to repeat this again. This generates a set of 100 two-dimension points randomly drawn from a normal distribution. They then scaled by 0.3. This scaling reduces the spread, creating points clustered around 0, 0. Now the x train np.r underscore x plus 2, x minus 2 forms two separate clusters by shifting points in x. The x plus 2 shifts all points by plus 2 in both dimensions, clustering them around 2, 2, whereas x minus 2 shifts all points by minus 2 in both dimensions, clustering them around minus 2, minus 2. The np.r underscore x plus 2 x minus 2 concatenates these two clusters vertically to create the x train. So let's go ahead and generate some test data with outliers. I'm going to say x underscore test np.r x plus 2 x minus 2 np.random uniform low equal to -6, high equal to +6, and size equal to 20, 2. This x test is combines the two clusters x in x plus 2 and x minus 2, same as the training data, with an additional set of 20 random outliers. Those are generated by that np.random.uniform, which generates 20 points randomly spread across a square region between -6 and 6 in each dimension. These points are more likely to be distant from the main clusters, making them potential outliers. Let's go ahead and initialize and train the model. First, I'm going to say model equal to isolation forest contamination equal to 0.1 and random state equal to 42. Now, this initializes the isolation forest model with contamination equal to 0.1, which specifies the proportion of data expected to be outliers. Setting it to 0.1 means the model assumes about 10% of the data points could be anomalies. Random state equal to 42 sets a random seed for reproducibility, ensuring that results remain consistent across runs. Then we're going to fit the model. Trains the isolation forest model on X train data. Next, go ahead and make some predictions. So here I am going to say model.predict x test. This uses the trained model to predict on x underscore test. In the context of isolation forest, predictions of 1 indicate points classified as normal or inliers. Predictions of -1 indicate points classified as anomalies or outliers. Let's go ahead and print this out. Here we print the predictions where each element in the prediction array is either 1, which is normal, or -1, which is anomaly, based on the model's classification. This allows us to see which points in X test the model flagged as outliers. Let's go ahead and run this project and save it. I'm going to open my command prompt and I'll say Python isolation forest.py, and there you go. We have our predictions depending on which points they were. Either they are outliers or inliers based on this. So I hope you are able to follow along and build this application or build this algorithm. If you had any issues, errors, or any questions, let me know and I'll get back to you. Convolutional neural networks, or CNNs. CNNs are deep learning models specifically designed for processing structured grid data, such as images. CNNs use convolutional layers that apply filters to the input image, capturing spatial hierarchies and features like edges, textures, and shapes. CNNs are widely used in computer vision tasks like image classification, object detection, and segmentation. Let's go ahead and implement this line by line in Python and understand convolutional neural networks. So I'm gonna already created a file here with which called cnns.py. I'm gonna first import the libraries. So first is TensorFlow STF. We'll be using TensorFlow, which is the main library for building and training deep learning models. We're gonna from TensorFlow.keras import layers and models. These modules within Keras with TensorFlow's high-level API for defining neural network layers and models. And then from TensorFlow Keras datasets, we're going to import MNIST. This imports the MNIST dataset from TensorFlow Keras datasets, which contains images of handwritten digits from 0 to 9. Let's go ahead and load and pre-process the MNIST dataset. So first, I'm going to say xtrain, ytrain, xtest, ytest. These two tuples are given to me from calling mnist.loadData. This loads the mnist dataset, splitting it into training and testing sets. Xtrain, ytrain are the training images and labels. Xtest and ytest are the testing images and labels. Next, I'm going to say xtrain, xtest is equal to xtrain divided by 255.0, xtest divided by 255 by 0. Here I'm normalizing the pixel values to a range of 0 to 1, improving the training process by scaling pixel intensity from 0 to 255 to 0 to 1. Next, xtrain equal to xtrain.reshape minus 1, 28, 28, 1. This reshapes xtrain to have a shape of number of samples, which is -1, 28, 28, 1. This reshaping prepares the data for the convolutional neural network, CNN in this case, where 28 by 28 is the image size and 1 represents the grayscale channel. Next, I'm going to say xtest equal to x underscore test dot reshape -1, 28, 28, 1. Similarly, reshapes the test data here. Now let's go ahead and define the CNN model. So first I'm going to say model equal to models sequential, and here I'm going to so what this does is it creates a sequential model where each layer is stacked in a particular sequence. So I'm going to write those in a particular sequence here. First, layers dot con 2d 32 comma 3 comma 3 comma activation equal to relu input shape equal to 28 comma 28 comma 1. This adds a 2D convolutional layer. Now in this 32 is the number of filters which are feature maps in the layer. 3 comma 3 is the size of the kernel that slides over the images to detect features. And then activation equal to ReLU. It applies the ReLU activation function to introduce non-linearity. Input underscore shape equal to 28 comma 28 comma 1. This specifies the input shape for the first layer. Next, I'm going to say layers dot max pooling 2d 2 comma 2. This adds a max pooling layer that reduces spatial dimensions by taking the maximum value in each 2 by 2 window, helping to downsample the feature maps and reduce computation. Next, I'm going to say layers.con 2d 64 comma 3 comma 3 comma activation value. Now this looks familiar. This again adds another convolutional layer with 64 filters this time, a 3 by 3 kernel, and ReLU activation. Again, something similar. Layers max pooling 2D 2,2. This again adds another max pooling layer to further reduce spatial dimension. Now, again, layers.conv 2D 64 3 by 3 and activation ReLU. This again adds a third convolutional layer with 64 filters and ReLU activation. Then I'm calling layers.flatten. This flattens that 2D matrix from the last convolutional layer into a 1D vector, preparing it for the fully connected layers. So now I'm going to go ahead and use dense layers.dense 64 comma activation ReLU. This fully connected dense layer with 64 neurons and ReLU activation. And then finally layers.dense comma 10 activation equal to softmax. This is the final output layer with 10 neurons, one for each digit class, which is 0 to 9, and softmax activation, which converts output into probabilities. Now let's go ahead, close it, and compile the model. So I'm move it up a little bit. In here, I'm going to say model.compile optimizer Adam loss equal to sparse categorical cross entropy matrix equal to accuracy. This model.compile, it configures the model for training. Optimizer equal to Adam uses the Adam optimizer, which combines the benefits of adaptive learning rates and momentum. The loss equal to sparse categorical cross entropy sets the loss function to sparse categorical cross entropy, which is suitable for multi-class classification with integer labels. And then matrix equal to accuracy at the end tracks the accuracy during training and evaluation. Let's go ahead and train the model. Model.fit xtrain ytrain epochs equal to 5, batch size 64, validation split equal to 0.2. This function model.fit trains the model on the training data. X underscore train y underscore train, the training data and labels. Epochs equal to 5. The model will go through the entire training set 5 times. Batch size 64 updates the model after every 64 samples, improving computational efficiency. Validation split equal to 0.2 reserves 20% of the training data for validation, allowing the model to evaluate performance on unseen data during training. Now let's go ahead and evaluate the model. For that, I'm going to say test underscore loss, comma test underscore accuracy equal to model dot evaluate x test y test. This evaluates the model on the test data and returns the loss and accuracy. X underscore test, y underscore test are the test data set and labels. Test underscore loss is the final loss on the test set, and test underscore ACC is the accuracy achieved by the model on the test set. Let's go and print the test accuracy, indicating how well the model generalizes to unseen data. Let's save it and go ahead and run it. I'm going to call it Python cnns.py. It's going to take some time because I'm going to run 5 epochs, which means it's going to go through the data set 5 times. So I'm going to just fast forward this part to the last. So we are in the last epoch here, almost training with all the 750. And there you go. We have our test accuracy. It is 0.988, which means almost 99% since 98.8. So it's pretty good. So as you can see, using the data set that we had, we trained this model and created a model that can kind of read handwritten numbers and tell us what number it is. So I hope you were able to follow along building this CNN algorithm. And if you had any issues, any problems, or have any questions, let me know and I'll get back to you. Recurrent neural networks, or RNNs. Recurrent neural networks are neural network designed for sequential data such as time series, language, or speech. RNNs have connections that form cycles, allowing them to retain information from previous steps in the sequence. This makes RNNs well suited for tasks like text generation, language modeling, and time series forecasting. A common variant or long short term memory LSTM helps to address the issue of long term dependency, which we'll look at in the next video. But for now, we're going to look at RNNs. So first, let's go ahead and implement line by line using Python recurrent neural networks. I've already created a file called as rnns.py. The first step is to import libraries. So I'm going to import the libraries. First one is TensorFlow STF. This is the main library for deep learning, providing tools to define and train neural networks. Next, I have layers and models from TensorFlow.keras. These keras modules in TensorFlow used to define the layers and structure of the neural network. Then IMDb, a dataset of movie reviews from TensorFlow's keras.datasets, with each review labeled as positive or negative sentiment. Sequence, a utility for pre-processing sequences specifically to pad or truncate sequences to the same length. This is from tensorflow.keras.preprocessing. Next, let's go ahead and load and pre-process the IMDb dataset. First, max features equal to 10,000. This is the vocabulary size, and max length is 500. The max features sets the vocabulary size to the top 10,000 most frequent words in the dataset. The max length limits each movie review to 500 words. Now, reviews longer than 500 words will be truncated, while shorter ones will be padded. So let's go ahead and next create the xtrain, ytrain, xtest, ytest equal to imdb dot load data number of words equal to max features. This loads the IMDb dataset, limiting it to max features, most frequent words. Xtrain and ytrain are the training data and labels. Each review is represented as a sequence of integers, which are word indices, and then xtest and ytest are test data and labels. Let's go ahead and say xtrain equal to sequence dot pad sequences x underscore train max length equal to max length. This pads or truncates each review in x underscore train to ensure all the reviews have exactly max length words. And x test equal to sequence dot pad sequences x test comma max length. This similarly, x test is padded or truncated to max length. This step ensures that each review is the same length, which is necessary for batch processing in neural networks. Let's go ahead and define the RNN model now. Model equal to models dot sequential, which defines a sequential model where each layer output is passed to the next layer. So let's go ahead and create the first layer. We have layers dot embedding max features comma 32 comma input length equal to max length. The embedding layer that converts word indices into dense vectors of fixed size is enabled here. The max features is the vocabulary size, limiting embedding to the top 10,000 words. 32 is the size of each word vector, which is the embedding dimension. And input length equal to max length. This is the length of the input sequences, which is 500 number of words per review. So once I've done that, I'm going to say layers.simple RNN with 32 as a parameter. This is simple RNN layer with 32 units, which processes the sequence data. Next, I have layers.dense, one activation equal to sigmoid. This is the output layer with one unit and a sigmoid activation function. The one is the parameter represents a single output neuron predicting the probability of a positive or negative sentiment. Activation equal to sigmoid. Sigmoid activation functions outputs a probability between 0 and 1 suitable for binary classification. Let's go ahead and close it and compile the model next. Move it a little up, model.compile, optimizer Adam, loss equal to binary cross entropy, metrics equal to accuracy. So here this configures the model for training. Optimizer equal to Adam uses the Adam optimizer, which adjusts learning rates based on momentum and adaptive learning rates. Loss equal to binary cross entropy. The binary cross entropy loss function is suitable for binary classification task, which is in this case sentiment analysis. Metrics equal to accuracy, which specifies accuracy as the evaluation metric. So let's go ahead and train the model. So to train the model, I'm going to say model.fit, which trains the model on the training data, where I'm passing x train, y train, which is the trailing data and labels, the training data and labels. Epochs equal to 5 is the number of times the model will go through the entire training data set. Batch size equal to 64, which is number of samples per batch for gradient updates, improving computational efficiency, and validation split equal to 0.2 reserves 20% of the training data for validation, allowing the model to evaluate performance on unseen data during training. Let's go ahead and evaluate the model now. Test loss, test accuracy equal to model.evaluate x test, y test, and I'm going to print the accuracy. So the model.evaluate function evaluates the model on the test set, returning the test loss and accuracy. The x underscore test, y underscore test, test are the test data and label. We have test loss, which is the calculated loss on the test data, and the test ACC is the accuracy of the model on the test data. And then finally print. So let's go ahead, save it, open your terminal and say python rnns.py. Run it. Again, it's going to do something similar as our previous project on CNNs, where it's going to run it for 5 epochs. So it's going to go ahead and run it first time. I'm going to fast forward it to the 5th time and then go from there. So we are almost done here. Let's see what is the accuracy that we get for the model for testing sentiment analysis, where we have written the algorithm using RNNs. So we should have it as soon as this completes the entire step here. And there you go. Test accuracy is 81%, which is not bad for sentiment analysis because it's much difficult sometimes based on the big data set that we have here to get the best option. And as you can see, it doesn't have much data, so this is pretty good as per the accuracy goes. Accuracy is 80%, loss is 53%. That's good. Higher the accuracy, better it is. So I hope you were able to follow along and implement this and you had similar results. If you see something else, errors, issues, or have any questions, let me know and I'll get back to you. Long short-term memory, LSTM. Long short-term memory LSTM networks are a type of RNN specifically designed to capture long-term dependencies in sequential data. LSTMs use gating mechanisms to control the flow of information, which helps prevent the vanishing gradient problem that standard RNNs suffer from. They are commonly used in tasks like language modeling, machine translation, and time series prediction. We did implement RNN in the previous video. In this one, we are going to do LSTM, which is almost similar to that code, but I'll still go through each and every line in Python implementing LSTM. So let's go ahead and write that code. So I have already created a file called as lstm.py. I'm going to start with importing the libraries. I have imported TensorFlow as TF, the main library for deep learning, providing tools for defining and training neural networks. We have layers and models. These are Keras modules which TensorFlow used to define layers and models for deep learning. IMDb is the dataset of movie reviews for sentiment analysis provided by TensorFlow's Keras module, where each review is labeled as either positive or negative. And then sequence, a utility for pre-processing sequences used here for padding or truncating sequences to a fixed length. Next, let's load and pre-process the IMDb dataset, where we have max features of 10,000 and max length is 500, same as last project, where max features sets the vocabulary size to the top 10,000 most frequent words in the dataset. Words outside this range will be ignored. Max length sets the maximum length of each movie review to 500 words. Reviews longer than 500 words will be truncated, while shorter ones will be padded. Next, I'm going to have xtrain, ytrain, xtest, ytest equal to IMDb, load data number of words equal to max features. This loads the IMDb dataset limited to the max features most frequent words. Xtrain, ytrain is the training data and labels, where each review is represented as a sequence of word indices. Xtest, ytest are the testing data and labels. So let's go get xtrain equal to sequence.pad sequences, xtrain comma max length equal to max length. This pads or truncates each review in the xtrain to make all reviews exactly max length 500 words in length. Similarly, for test, we run the same command sequence.pad sequences xtest max length equal to max length. Similarly, pads or truncates xtest reviews to a uniform length. This step is necessary for efficient batch processing in neural networks. Now is the real LSTM model. So let's define the LSTM model. Model equal to model.sequential. This creates a sequential model where each layer's output is fed directly into the next. Layers.embedding max features 32, input length equal to max length. Embedding layers that converts word indices into dense vectors of fixed size. The max features again is the limits the embedding layer to the top 10,000 most frequent words. 32 is the sets the size of each word vector to 32 dimensions, and input length equal to max length defines the max length of input sequences to 500 word, ensuring all inputs are consistent in shape. Now let's go ahead, and here is where we add LSTM. Layers.lstm 32. Long short-term memory LSTM layers with 32 units. LSTMs are designed to capture sequential dependencies in the data, making them well suited for text. Layers.dense 1, activation sigmoid. Fully connected output layers with one neuron and a sigmoid activation function. One here is a single output neuron predicting the probability of positive or negative sentiment. Activation equal to sigmoid is a sigmoid function to output a probability between 0 and 1 suitable for binary classification. Next, let's go ahead, close it, and compile the model. When I compile the model, I'm going to say model.compile. Again, I'm going to use the same things: optimizer equal to Adam, loss equal to binary cross entropy, and metrics equal to accuracy. Where model.compile configures the model for training, optimizer Adam uses the Adam optimizer, which adjusts learning rates dynamically and is widely used for deep learning. Loss equal to binary cross entropy is binary cross entropy loss, which is appropriate for binary classification task. And finally, metrics equal to accuracy tracks the accuracy during the training and evaluation. Let's go ahead and train the model now. So train the model, model.fit, pass xtrain, ytrain, epochs equal to 5, batch size 64, validation split equal to 0.2. Here xtrain and ytrain are the training data and labels. Epochs equal to 5 is number of times the model will iterate over the entire training data set. Batch size equal to 64, number of samples processed per training batch. This helps manage memory and improve computational efficiency. Validation split equal to 0.2 reserves 20% of the training data for validation, allowing the model to evaluate performance on a validation set after each epoch. And now let's go ahead and evaluate the model. Test loss, test accuracy equal to model.evaluate x test y test. This evaluates the model on the test set, returning the test loss and accuracy. X test and y test here are the test data and labels. Test loss is the loss computed on the test data. Test accuracy is the accuracy achieved by model on the test set. Let's go ahead and print our test accuracy, which prints the test accuracy showing the model generalization performance on unseen data. I'm going to save this, open my command prompt, and say python lstm.py. Again, it's going to run for 5 epochs. So I'm going to, as soon as it starts with the first epoch, I'm going to pause it and fast forward to the 5th epoch. So now that we are done with our 5 epochs, we can see the value accuracy at the end of it was, depending on each epoch, you see it's an average of 86%. And now we're going to probably test the final accuracy, which is around 86%. With RNNs, it was 81%, whereas with LSTM, it's 86%. If you have not seen the RNN video, you can go to the previous one and check it out. But as you can see, with LSTM, we got a better accuracy from for the same data set for IMDb. If you are able to solve this, perfect. If not, if you had any issues, errors, or problems, let me know in the comments and I'll get back to you. This is the last machine learning algorithm that we'll be looking at in this particular series. Transformers are deep learning architecture designed for handling sequential data without relying on recurrence, which is commonly used in RNNs. Instead, transformers use a mechanism called self-attention to process all tokens in the sequence simultaneously, capturing dependencies between tokens regardless of their distance in the sequence. Transformers have become the foundation of many NLP tasks and models, including BERT and GPTs. Let's go ahead and implement transformers using Python, and I'm going to go over each line of code as and we go through it. So first, I've created a file called as transformers.py. Here, I'm going to first import the necessary libraries. TensorFlow, STF. This is the main library for building and training deep learning models. Layers from TensorFlow.keras is the Keras module for creating different types of neural network layers. IMDb, Keras module for loading the IMDb dataset used for sentiment analysis, classifying movie reviews as positive or negative. Then sequence from TensorFlow Keras.preprocessing is a Keras utility for preprocessing sequence data, especially useful for padding or truncating sequences to a uniform length. Let's go ahead and load and preprocess the IMDb dataset. First, I'm going to set max features equal to 10,000, max length equal to 200. Now, the max features limits the vocabulary to the 10,000 most frequent words in the dataset. Any words not in the top 10,000 are ignored. Max length is 200. It restricts each movie reviews to 200 words, truncating longer reviews and padding shorter ones. Next, we are going to say xtrain, ytrain, xtest, ytest equal to IMDb load data number of words equal to max features. This function loads the IMDb dataset, returning the top max feature words. The xtrain and ytrain are the training data and labels, whereas xtest and ytest are the testing data and labels. Next, I'm going to say xtrain equal to sequence dot pad sequences, xtrain max length equal to max length. This pads or truncates each review in the xtrain to make all reviews have exactly max underscore length words required for efficient batch processing in neural networks. Next, I'm going to do the same thing with xtest, which pads or truncates xtest reviews to a length of 200 words, which is our max length variable. Define a transformer block. Now here we're going to create a transformer block. So we're going to start with calling it class transformer block layers.layer. This particular thing defines a custom layer representing a transformer block. I'm going to write the initializer method, and it needs self embed dim number of heads ffdim rate equal to 0 1. This is the constructor method where self is its own object and embed dim is the embedding dimension for each word vector. Number of heads is the number of attention heads in the multi-head attention layer. ffdim is the number of units in the feed forward layer, and rate is the dropout rate to prevent overfitting. Next, I'm going to call the super method of the initializer, and then I'm going to say self.att equal to layers multi-head attention number of heads equal to number of heads key dim equal to embed dim. So this is multi-head self-attention mechanism to learn contextual relationship in the input data. Next, I'm going to say self.ffn equal to tf.keras sequential. This defines a feed-forward neural network FFN layer with a dense layer, this one, first one, with FFDIM until units and ReLU activation. We have another dense layer with embed dim units returning the same dimension as the input. Next, let's close it out and create the self layer norm1 equal to layers.layer normalization, epsilon equal to 1 raised to 6, layer norm2, same thing that I'm going to do. These are layer normalization layers to stabilize and improve model performance. Next, we have self.dropout1 and self.dropout2 layers dropout rate. Dropout layers to randomly drop units during training, reducing overfitting. Next, let's create a function called as call. This takes takes parameters of self inputs and training equal to none. This defines the forward pass for the transformer block, where we'll create attn output equal to self.att inputs. This applies self attention, allowing the model to consider each word in the context of the others. Attn output equal to self.dropout1 attn output training applies dropout during training to the attention output. Out1 self.layer norm1 input plus ATTN output. This adds the attention output to the original input and normalizes. FFN output equal to self.ffn out1 passes the normalized output through the feed forward network. We create ffn output self.dropout to ffn output comma training equal to training. This applies dropout to the feed forward network output. And finally, we return the self dot layer norm to out1 plus ffn output. So this adds the feed forward network output to out1 and applies normalization for the final output. Let's go ahead and define the model. For this, I'm going to use the embedding layer, a number of heads, and ff dim equal to 32. So first one is the embedding dimension of each word vector. The number of heads is in the multi-head attention layer is the num underscore heads, which is 2, and ff dim equal to 32, which is units in the feed forward network. Let's go ahead and say inputs equal to layer dot input shape of max length comma. This inputs layer equal to layer dot input is an input layer accepting sequence of length max underscore length. Next, we're going to create the embedding layer. Layers equal to embedding input dim equal to max features, output dim equal to embed dim, and input length equal to max length. This is an embedding layer that maps word indices to dense vector of size embed underscore dim. Next, we're going to create x equal to embedding underscore layer inputs. This passes input sequences through the embedding layer. Transformer block equal to transformer block embed dim, number of heads, and ff dim. This initializes the transformer block with specified dimensions. X equal to transformer block x comma training equal to true applies the transformer block to x, explicitly setting training equal to true. X equal to layers global average pooling 1D x. This reduces each sequence's dimension by averaging across the time axis. X equal to layers dropout 0.1 and x applies dropout with a 10% rate, that's why 0.1. X layer dense 20 activation equal ReLU. It's a fully connected layer with 20 units and ReLU activation. X equal to layers dropout of 0.1x is applied dropout to the dense layer again with 10% rate. Output equal to layers dense 1 activation sigmoid as x. This output layer with a single unit and sigmoid activation for binary classification. Now let's go ahead and compile the model. Model equal to tf.keras model, inputs equal to inputs and outputs equal to outputs. So this creates a keras model object from the input and the output that we created earlier. Then I'm going to say compile and train the model. Model.compile optimizer Adam loss equal to binary cross entropy and metrics equal to accuracy. This configures the model for training. Optimizer Adam uses Adam optimizer, which dynamically adjusts learning rates. Binary cross entropy loss for binary classification is used here, and metrics measures accuracy during training and evaluation. So let's go ahead and train the model. So model.fit x underscore train y train batch size 64 epochs 3 validation split equal to 0.2. This will train the model on the training data. X train, Y train are the training data and labels. Batch size 64 processes 64 samples per training batch. Epochs 3 is the model goes through the entire data set 3 times. Validation split equal to 0.2, which reserves 20% of the training data for validation. Next, let's go ahead and evaluate the model. Test loss, test accuracy, model.evaluate, x test, comma y test. This evaluates the model on the test set. The test loss is the computed loss of the test data, and the test accuracy is the accuracy of the model on the test data. Now let's go ahead and print this. So this is the entire algorithm of how to implement transformers in your code, and they're all coming from some of the TensorFlow libraries for you to use. So it's pretty straightforward, pretty easy to implement, only 60 lines of code. Let's go ahead and run it first to check if it actually works. I'm going to go ahead and say Python transformers.py, run it again. This time I've given only 3 epochs, so it will be faster, but again I'll still forward it to the third epoch and continue from there. So we have completed with our three epochs, and now to calculate the accuracy overall, we can see the accuracy is almost 86%, 8591. That's pretty good, and that's how you can implement transformers using Python. If you had any issues or any problems implementing this or have any questions, let me know in the comments and I'll get back to you.